think. Okay, yes. So we are live. We are getting off to something of a late start. Uh, how are you doing? Hello? Amos? Are you there? Uh, I can't hear you if you're, I don't know if you can hear me. Hello? Amos? Are you around? What's up? Amos, are you there? Can you hear me? Okay.
Can you hear me?
There you go. Okay. Here you are.
Oh crap! I forgot we're on Parsec.
Yes. Yes,
Yeah.
you do want to
I'm
be
happy.
you want to be aware of that, right? I mean, I don't know. I almost was like, should I disconnect this? I almost did, but
Right.
it's pain
Yeah.
reconnecting it. So just be aware, like once you've connected to me on Parsec and I'm streaming it, there's sort of a permanent record of your screen online. Nobody's really looking at these streams, etc. at the moment. So, but you do want to be aware of that. I'm a little bit unsure about the implications of your. I'm a little bit unsure about the implications of that Discord QR code appearing.
Hmm.
So might want to look into if there's a way to, like, I don't know, invalidate Discord QR tags. It's really unlikely that anything would come of that, but it is, it's something to be aware of.
Yeah, yeah, definitely.
Generally, I would not look at your email at all when you're connected to be on Parsec and I'm streaming.
Well,
Just avoid
yeah,
it.
my problem is, yeah, totally. The problem was that I had to reset my passwords for
Gotcha,
sending the
gotcha. You don't have a second monitor.
relay.
You don't have a second monitor, I take it.
No.
Nope. Okay. Okay. Well, I don't think it's a particularly big deal, but I might take a look at that QR code thing. Um,
Yeah.
but anyway, won't worry too much about it. We are lagging pretty badly, um, but maybe if you want to, like, pop open the Doctor Racket and full screen it, and we can take a look at where we were.
Okay. Hopefully we can get started now.
Yeah, little rocky, but that's all
Yeah.
right. That's all right. So let's see. Do you have the last session open?
Unfortunately, no, because I did not save it properly, so it's gone. This is
Okay.
the one before.
Okay.
Yeah.
Alrighty. Okay. Well, that's not a big deal. So I'm just thinking about this. So last time, I think maybe we should just go over a little bit of stuff, like, again, just to try to refresh it. I do think we need to maybe think about something in order to try to keep you a little bit fresher. A week is a really long time. And so
Hmm.
I feel like we're going over a lot of the same ground, like, kind of over and over again. And, like, eventually it'll stick, but it's not a particularly time efficient thing to do, right?
Yeah. Yeah.
Especially
Totally.
since it felt to me like there's a lot of this stuff that you pretty much understood the first time, that we got on. And so, which was, like, more than a month ago. And now, but it's stuff that I think we still kind of have to go back over. But let's talk about lambdas first of all. Again, do you remember our friend Lambda?
I think so.
Okay.
Yeah. Special function. Special function.
Special form. Yep.
Special form.
It is a
Right.
special form. Um, and so if you wanted to use lambda to sort of create a function, say that, like, multiplied something by 10 and added 7, how would you go about doing that? Can you sort of use lambda to create one of those and then apply it to a number all on one line?
Um,
Or you can just, like, write out the lambda first and then worry about applying it later.
thing is the. So what we're doing, we're multiplying by 10 and adding 7.
Yeah, I wouldn't worry too much about that, but sure, that seems reasonable. It's not a particularly the details of that particular function are not terribly important.
The other. Jake. No, it doesn't. It's just.
Right. Yep.
Uh, first, you have to. Just copy the other thing. Oops. No, X has to be in there somewhere. Um, isn't it? Yeah. Right, and then, but if I wanted to wouldn't I, want to
You have an extra. You're missing a space between the plus sign and the 10. It's reading as just one symbol.
right, thank you. So are we gonna get 52? Wait, why is it yellow underneath? Warning, definitions window has changed. Oh,
I think that's because you have stuff. You have an old session up there. You actually may want to be working like in a fresh REPL.
Oh, yeah.
Right.
Okay.
You might want to open another window and sort of maximize that. And then you remember we went through this whole thing about sort of titling the windows last time. But and it'd be kind of nice to have that to refer to because I think we do just want to take a quick look at some of the stuff in there. But we're not going to want to execute that entire thing up there because it would execute every single command in it, and there's a whole bunch of them. So
yeah. So it'll do that even if I haven't run up top here?
No, it won't, but that's what it's warning you about. And at some point, I mean, we could keep working in this REPL, but we're going to want to actually work in the top window at some point as well.
Yeah.
Right? That's typically where you actually do most of your work is the top window. Like, we're still just sort of exploring stuff, so we're typing a lot of stuff in at the REPL at the moment. But, and the top window is typically a more persistent thing in that you can save these sessions as you have. But usually you don't save your REPL sessions. It's not like, you always save your top window. That's where you rate your programs.
Right.
So.
Well, let me, and then I should be able to.
Yeah, there you go. It's a brand.
Well, but then this into the lag situation.
It's going to lag a little bit when you flip back to the other one. It would be kind of nice to tile them, but we can maybe worry about that.
To title them?
To tile them? Get them both get them both on the screen, not overlapping each other, but with enough space to see both of them.
Yeah.
Because at the moment it's a lot wider than it has to be. So if you had them laid out horizontally, I know that we had some trouble with that though the last time we tried.
Well, I think that's gonna. Why is it not allowing you to grab the thing?
It might increase lag a little bit too. Yeah.
Yeah,
I think mostly it would still work reasonably well because but it is a lot more when you have it full screened. It is just sort of a big black entity, and that is kind of nice. So this will do. We don't need the other one to refer to really all that much. We can just sort of look at some stuff. So, okay, so yeah, why don't you type that out again, that lambda, and apply. Don't apply it to anything. Just type it out again.
Wait, let me get my thing first. My argument list, right? No, yeah.
Yep.
That's the argument list.
That is right.
And to the product of X7. So, and then procedure.
Return. You get a procedure. Now, if you wanted to bind that to a name, how would you type that out? Say you wanted to bind it out to like Scratch Procedure 1 or something.
It's a long name.
It is. Okay.
Right?
Yep. And then you type out the lambda.
Yeah, same deal.
Okay. Now, what if you wanted to use define to define Scratch Procedure 2 that did exactly the same thing, but without using a lambda, using the special syntax of define? Do you recall how that would go?
It doesn't let me go back and change the thing, huh? Why is it? Because I realized I just put Scratch. Yeah, how is that?
Yeah, I mean, once you've put it in, you've put it in. right?
Yeah,
Like
I guess so.
that's what the REPL. Well, it would be misleading if you could go back and edit it because the state of your REPL is to a large degree determined by what you've put in before. So if you
Yeah.
went back and fixed it up there, it wouldn't actually change the name that you'd defined, right? Because when you defined it, you actually made a change to the environment.
Environment, yeah.
There are ways
Okay.
to actually remove functions from environments, I would imagine, in Racket. There certainly are in most Lisps, but that's, yeah, we don't want to worry about that.
So, okay, so we're gonna have a define scratch procedure 2 without using a lambda.
Without using the lambda.
I'm gonna start off with the define. I'm gonna miss.
Gonna be consistent in misspelling
It,
it.
yeah, I figure that's more important then.
Yeah.
So it's not a,
Okay.
so the syntax is not using a different special form, I don't think. I'm trying to
Well, it's
remember.
still define, and define is the special form, but it
Okay.
uses slightly different syntax. So let's just go over this because this is how you usually want to define procedures. So
Yeah.
the way that this works is you basically, so you see how the lambda has three parts, right? It's got the lambda, it's got the argument list,
Yep.
and then it has the body.
Yep.
This basically works pretty much the same way, except that there is no lambda, right? It's just
Yeah.
the define is now sort of right, is now
Mhm.
the thing that you're doing. There's no internal thing. And then you take the name that you want to name the function and you make that the very first thing in your argument list.
Right.
And then everything else is exactly the same. Well, no. You don't need another define. You don't need another define. You just need the one define. But what I'm saying is this define now has three parts. It has a define, it has an argument list, and it has a body.
Gotcha. So
And the
that
first thing in the argument list is the name of that you want to name the function.
so I already did the argument.
But it has
No.
to be an argument list. Has to be an argument list. So you see how your argument list is like a list that contains X? Now it
Yeah.
would be a list that contains the name of the function and X.
Oh.
Okay. You already have the name of the function though. So you don't need the name of the function twice.
Oh, okay. So it doesn't need another.
It needs a paren to begin the list before
Gotcha.
the name. But that's sort of how you can go about remembering how this works, is that you basically just have the argument list with the name of the function as the first thing in it, and then your arguments.
So, but this doesn't. I mean, okay, right. So now I will be able to call the procedure by using the name bound to it stretch procedure 2.
Mm-hmm. I mean, the effects of doing this are basically exactly the same as doing it with a lambda.
Yeah.
It's just,
But it would be an added thing that you now have it defined that in a way that you can call it on future.
well, right, but you did in the line just above there where you used to define to bind that name to a lambda, you could too. This is essentially exactly the same as doing it that way. It's just a little less syntax. It's, what we talked about syntactic sugar before. This is just syntactic sugar. What you're doing here is exactly the same as the line above, except that it's a different name. It's, stretch procedure 2 instead of stretch procedure 1. So yeah. Go ahead and hit return. Let me see. I think you did get your parens there, right? Yeah, it looks right. Yeah, so try calling it.
Whoops. Oh, it's to close the paren. Why did it skip a line?
Yeah, there you go. Because you would hit return already. You sort of created an extra line when you did that. So it was like, I'm not going to step on that line you created, I guess.
Yeah.
So there's something important to notice here that we've talked about a little bit, but I'm just going to mention it again, which is typically if you leave special forms out of the question, Scheme has this incredibly regular syntax that has an extremely small number of rules, right? It has some rules for how you evaluate certain things, and then it's got, I mean, that's really all it is a bunch of rules about how you evaluate it. Most things kind of, numbers will evaluate to themselves, symbols evaluate to whatever they're bound to in the environment, strings evaluate to themselves. And then if you see an open paren, then that means that you're about to apply a procedure. So the thing right after it basically gets evaluated, and it is supposed to evaluate to a procedure. Note that procedures themselves evaluate to themselves. So you can actually have. Do you see what I mean by that?
So when I open paren define the procedure,
Well, I'm
it's
talking about in the absence of special forms. I'm just talking about what scheme's rules are if you ignore the existence of special forms. So define's just not even in our universe of discourse at the moment.
okay.
Okay, but I'm just
But
talking
you're
about
saying
scheme rules.
procedure evaluates to itself as a procedure?
Evaluates to itself as a procedure. So if you have a procedure, let's say you have somewhere stored a procedure, which we saw how to do last time, like a procedure itself, not the symbol that it's bound to, not the symbol that's bound to it, I mean, but the procedure itself you can store in a list. If you have that in a list and you pull it out of the list, for instance, if you just have a procedure on hand and you use that after an open paren, that works too. The reason it works is the procedures evaluate to themselves, basically, right?
Yes.
There is this rule that whatever comes after that open paren is going to get evaluated, and it is going to it needs to evaluate to a procedure. So if it's a procedure that's after that open paren, it's okay because the procedure gets evaluated. It evaluates to itself. Itself is a procedure. But note that there is kind of that little step there, right? But yeah, so that's really all the rules there are in Scheme. And then there's just like some rules about how to evaluate certain types of things. That's it. That's all of the syntax of Scheme if you ignore special forms.
Okay.
But I mean, it's an incredibly simple language, basically. Well, there's reader symbols too, and we looked slightly at those. So, quote, for instance, with just the single quote, is that did I say reader symbols? Reader special forms. They're still a kind of special form, though. Reader macros is what they would be called in Common Lisp, but I don't think they are in Scheme. But anyway. However, special forms bring. So that's one nice thing about Scheme is that once you kind of understand like the syntax of Scheme, there isn't any of it, right? You can explain the syntax of Scheme, leaving aside the special forms. You can explain the syntax of Scheme to somebody in 5 minutes. Now they might not actually quite internalize all of it, but like you can write it down practically on a piece of paper. Special forms, though, change things because special forms have their own internal syntax, right? And everything that's inside the body of a special form does not have to follow Scheme's syntax rules. And you can see that with the lambda that you typed right at the beginning. You have open paren lambda. Okay, so it's evaluating this, and it's a special form, not a procedure. But okay, we'll say that's another part of the syntax is that this can be a special form as well. But then the very next thing you have is open paren x.
Yeah.
But x, what is x? Is x something that can be evaluated to a procedure?
No, it's not anything at that point.
It's not. It's a symbol, but it's not. It's not a symbol that's bound to anything.
Right.
So if you were to try to evaluate like open paren x close paren, right? If you were to type that right now, you'd get an error because it would be like what is x?
Yeah.
But that doesn't happen in the body of the lambda. And the reason that it doesn't is because lambda is a special form and it has its own syntax and it can do whatever it wants with that syntax, right? Somebody wrote lambda and you can write your own special forms, although it'll be a little while before we take a look at that. We might even be in a different language because I think we might at some point want to move on to Clojure, which is a Lisp and is quite similar to Scheme in many respects, but has some, really significant differences too. The syntax is very similar though. But let's say you're writing your own special form, like you can do pretty much anything you want to in there. And we talked a little bit about how special forms, one of the things that is special about them is they can control the evaluation of their arguments, things inside it. They control whether it gets evaluated. So it's okay for that X to be there. It can not evaluate X, right? Yep. You could not pass X as an argument to any function without it blowing up right now, right? Because you remember we talked about this. Argument to a procedure, and I should be careful about my terminology there. A procedure, not a function. But you can't, at this point, you cannot use X as an argument to any procedure, no matter what that procedure is, because arguments get evaluated before they get passed to procedures. And X is not bound in
the outside environment.
In your top level environment. And so it would blow up before that procedure ever even got invoked. Right? But special forms are special. They can do whatever they want to. And So somebody writes them and decides how they're going to work and actually has to write
Hmm.
code, which might very well be written essentially in Scheme itself. There could be some primitive things, that's kind of up the internals of the interpreter. So we don't actually know the implementation details unless we go look up Racket's source code.
Yep.
But almost all these things, you could think of them, if you have some other primitives to work with, you could think of them as being written in Scheme. And indeed, that is one way to create new special forms, is to write Scheme code that takes in some things, some lists, basically, and then is able to produce whatever code it wants to and kind of substitute that code in place when you invoke them. So I'm being a little long-winded here. I do want to kind of emphasize that. It is kind of an important, subtle point that's pretty easy to miss. But let's note something about this second form of define, which is that it's actually very different in terms of what it takes. It looks pretty similar in a way, right? It's got these three parts. But the second part is a list instead of a symbol.
Hmm.
It's a different type of thing. And that's what tells it, hey, we're not doing the normal thing of just binding a value to a top level name. What we are doing is we're going to use a lambda, right? Do you see what I'm saying here?
Yeah, is that just because of the parens there?
Yeah, pretty much. That's how somebody wrote it. They said, we're going to make this special syntax for this. And the syntax is we have define, and define
Yep.
does this very straightforward thing, which is it binds a value to a symbol. We'd also like to have a define that allows you to simplify, binding procedures to names. We want you to be able to, to write it out the way that it's written out there without having to do lambda and all that rigmarole. So they're like, okay, we'll just sort of, and because it's a special form and they're writing the special form, and you can do practically anything in a special form, right? You have a lot of power there. You're like, you know what? The way that we want this to work is we want this syntax to be like this. You do the define, and then if if it's just a symbol, then we're just going to bind something to that symbol. But if it's a list, we're going to say this is an argument list that starts with the name that we want to bind the procedure to, and then the next thing is actually going to be a body, and we're going to behind the scenes rearrange that into a lambda, and we're going to bind it to the name. Fair enough.
Yeah. So in this one, yeah, right. I could have as many argument lists.
You could have as many arguments in the list as you wanted.
Yeah.
Yeah, you couldn't have as many argument lists as you wanted. You get one argument list. You can actually, and we've seen this, just for completeness, I'll mention it again. You can have more than one form in the body. And if you do, it's the same thing with the body of a lambda. A lambda can have more than one form as the body. It can have multiple bodies. And each of those, form is actually really kind of the wrong word here. I'm being a little imprecise, but it can have more than one thing in the body, and they get evaluated in turn, and then the value of the last one is returned if that's what happened. And so the only way that that's actually useful or interesting to do is if the things that aren't the last thing in the body have side effects, right? Because their return value is being thrown away. So if it's something, and almost everything that we've written in terms of bodies of lambda has been what we would say has been pure, in the sense that it does not cause side effects. And really, other than these special forms, obviously define, for instance, has side effects. It changes something, a binding in the top level environment. That is a side effect. And so other than a few special forms, though, the only thing we've really looked at that has side effects, I think, is printline, right? But printline has a side effect. It prints something, and that is a side effect. Note, though, that when you just evaluate an expression, like if you evaluate x times 10, right? Like, open paren times x 10. You see whatever, if x is 5, you'll see 50 get printed at the REPL, right? But you aren't printing it. The REPL is printing it. So your expression is pure. It has a side effect. Executing that, putting that into the REPL and hitting return does cause a side effect to happen, but it's not your code that's causing that side effect. So your expression, whatever it is, times x 10, or just times 510, that's pure, right? If that were the body of a function, we'd say that it is a pure function. It really doesn't make sense to talk about pure outside the context of functions, but procedures.
The side effect when the REPL prints 50, why is that a side effect? Because it's changed.
Because you printed something. You changed the state of the REPL. It is, I'm going to say, like, any change to the world that you or I can observe is a side effect.
Okay.
Right? It actually causes, an output is definitely a side effect.
All right. Yeah. Okay.
So, but if you type in print line 50 or 52, try doing that. Like print 52.
Wait, does that adds the I, right?
Yeah, that's right. Okay. Do you see how it printed in a different color?
Hmm.
That's to tell you that you printed it and not that it wasn't the REPL that did this, that you did that, right?
Interesting.
Because print line, when you evaluate print line, what you get is basically the absence of a value. That's what print line returns, returns basically is the absence of a value.
And is that the thing, like with quote, that it's that special form stops evaluation?
No, this is different. Print line got evaluated.
Well, yeah, it would have to know the 52 is there to.
Yeah, it's just the print line doesn't evaluate to anything really. It evaluates to the absence of a value, basically. That is a thing you can do. If you type in open paren values close paren right now.
Values.
Yeah, just values. That also evaluates basically to the absence of value. If you type in open paren values 5. Okay. So that's as if you evaluated a function that returned 5. And you can actually have more than one values. And there are procedures that actually return more than one thing, essentially, as well. So we won't get too deeply into that right now. But you can see that this is another thing that just evaluates to Now, that's different from nil, right? If you type in nil right now, just nil, not as a function. It's not a procedure. Yeah. Oh, is it not that? Is it null? What is it? What is it in Racket here? Well, no, it would have 2 L's. There you go. Okay, it's null. I'm sorry. I'm getting my Lisps confused.
So isn't that a list? No.
It is the empty list. So null is basically the empty list. It is a value that represents nothing. Note that a value that represents nothing is different from the absence of a value. It is still a value.
Mm-hmm.
Okay. Again, a slightly weird, subtle distinction, but there is a distinction between there not being any value and having a value that represents nothing. And null is the value that represents nothing. And it is a synonym for the empty list. The empty list also represents nothing because it's a list with nothing in it, basically.
Mm-hmm.
So we talked about that. We talked about list summon. Do you remember car and cdr?
Yeah. Car
and first and rest, really, which is what we most of the time prefer to call them.
Got it. Returns the first item in the list, and rest takes away the first item and returns everything else.
That's right. And so the types, note that the types of those two things are going to be different most of the time, unless you have a list of lists, right? But if you have a list of numbers, for instance, first is going to return a number, right? If you call it with that list. Whereas rest is going to return another list. Rest always returns another list. Whereas first returns something of the type of the first thing in the list, right? So we talk about scheme and we say that scheme is dynamically typed as opposed to a statically typed language. And so you haven't really used a statically typed language, and I don't want to get too deeply into it, but there are some languages in which you have to indicate to the language what the type of everything is while you're writing the program. You have to say, so not only do I have, it wouldn't be a symbol in most languages, you'd call it a variable. This term symbol and the way that we're using it isn't what you would call it in all languages, I would say. But like a variable, for instance, if you have a variable x, in some languages, just to declare that variable, you would have to say x is an integer. It is of that type, right? Mm-hmm. That's a very common thing in statically typed languages. Used to be very much the norm for pretty much all programming. Like dynamically typed languages were pretty weird at one point. And gradually they've become... people still use quite a lot of statically typed languages. Both Java and C++ are statically typed, and they're both they're both heavily used. But a whole bunch of the world has kind of moved into languages like, especially like Python and JavaScript are both very, very popular languages, and they're dynamically typed. So The thing to remember, though, is that just...
Hey, what's Java? I thought you just used Java as both.
Yeah, that's confusing. And it's really
Not
kind of
that.
foolish. Java and JavaScript are two completely different languages
Oh,
that have absolutely nothing to do with each other. It was a marketing thing. When JavaScript was invented, it was very shortly after Java had been introduced, and Java was a language developed by a company called Sun Microsystems, which is gone now. Oracle bought them. But Sun was this enormous behemoth of a company, like in the early 90s.
that reminds me of Oracle.
I'm sorry?
Reminds me that I wanted to look up Oracle because I met someone who said their father was a co-founder.
You met someone who said their father was the co-founder?
Yeah,
Are they Italian?
I'll tell you about it later.
Okay, that's really interesting because my mother was pretty close friends with the co-founder of Oracle. There may have been more than one co-founder, but this was the guy who was basically, and he died really young.
Okay,
What was his
different.
last name? He was Italian. I forget now, but yeah, my mom was. So I wonder if this is the child of of basically an old friend of my mother. It's kind of interesting. Okay.
Yeah, I don't think so. But I'm gonna make a note. We should chat about it. But uh, okay. So yeah, we were saying static, and so static. The variable, the type has to be fixed, but it could be multiple kinds of type. You just have to tell it what you're working in at that moment. Or something.
So this gets pretty complicated, and it depends on languages. For the most part, no. It's like in a language like Java, it's just no. It's a type. It's like X is an integer. That's what X is. Like you have to, if you try to assign something that isn't an integer to it, like bad things will happen. And we won't worry too much about why you would want things to be statically typed versus dynamically typed. There are pros and cons, and that's kind of a long discussion. And people tend to get pretty religious about this. Some people really think that dynamic typing is evil. Some people think static typing is evil. Type systems get very, very complicated. The thing to remember about Scheme, though, is that even though the types aren't static, you don't have to define them, and you can indeed bind some, you can have a particular symbol that's bound to one type of variable, and you could rebind it, for instance, to a different type of variable. Yeah, well, to one type of variable, to a value with a certain type. You could rebind it to a different value with a different type. You can do that kind of thing. There's also strongly typed and weakly typed, and I won't get into that too much. A lot of people get these kind of confused and will say that a language like Scheme is a weakly typed language, and they mean dynamically typed. Scheme is actually a fairly strongly typed language compared to a language like C. In that you can't treat types as if they were other type, as if they were a different type very easily in Scheme. You can in some ways. You can multiply a floating point number by an integer. And so, that's really common. There are languages in which you can't really do that, though. If you're programming in Haskell, for instance, which is a very strongly typed language and is also statically typed, if you try to multiply an integer by a floating point number, you will get a type error because multiplication is not defined for integers and floating point numbers. You'd have to turn the integer into a floating point number or the floating point number into an integer and then multiply them. But Haskell is very, very strict. Most languages do have what we call a numeric tower, where we have talked about this a little bit, that the types of numbers sort of nest inside each other, right? You have your counting numbers, and then you have your sort of integers, and then you have your rational numbers, and then you have your irrational numbers, and as we go up, each one of those is an interior Kachinkadal, and they all get subsumed under the larger ones. And then there's even, I think I looked this up, but Scheme also has complex numbers, right? So all the real numbers fit inside the complex numbers, and then there's a whole bunch of other numbers that are not real numbers that are also in the complex numbers. Right? We briefly touched on that, right? That there is the real numbers are a number line. You can think of the complex numbers as forming the complex plane. Right?
Mm-hmm.
There's a whole bunch of sort of parallel sets of numbers parallel to the real plane. I say a whole bunch.
Are they parallel? They don't have to.
Yes, there are a whole bunch of them that are parallel. They sort of get put up in rows. Yeah, they're parallel. So
Okay, they can't. Yeah. Anyways, that's
right.
I don't have much. That is not much. I can kind of place that information, but then not really.
Yeah, you don't need to do that much with it now. If we were to do some stuff like, say, try to draw the Mandelbrot set, which might be a kind of fun thing to do, actually. You use complex numbers, for instance, trying to draw the Mandelbrot set.
Mm-hmm. Cool.
But anyway, but that is a little bit of a misconception. Scheme is a very strongly typed language. It's just not statically typed. And so it's important. I'm being a little long-winded here, but this is, I think, kind of an important idea. It's important to think about the types of things in Scheme. And types really matter a lot, actually. And having types straight in your head, what the types of things are, can really actually help you think through stuff, and kind of keep your bearings as to where you are. And so, because if you try to use something of the wrong type, like if you type in plus and then like the string high and then the string there, like try that out. Try adding the string high to the string there. Right. That's going to blow up because it is of the wrong type. The type it expects is a number. So it's important, first of all, to know the types of things, so you know what operations you can perform on them, which is pretty close to a definition of what a type is in a way. But it also, it helps to keep your bearings. And so one of the things that I was just talking about is, right, first has the type. It's whatever the first thing in the list is. We don't know what its type is because we don't know what that is, but the type of rest is always type list. Right, rest cannot return you anything except a list.
Even if it's just one number, or I suppose even no numbers. But if your list was just one number and you asked for rest, it would just return an empty list.
It would, and in Scheme, it's an error to call rest on the empty list. There are other Lisps in which doing that will actually just give you another empty list. You can keep calling it on it. You just keep getting an empty list, but you cannot do that in Scheme. It's just an error to do that. So it's always going to give you back a list. Whereas, first, you don't know what it's going to give you back. It could give you back a list if you have a list that the first thing in it is another list, right? So we were talking last time a little bit about constructing lists. Do you recall how to just make a list all at once out of a whole bunch of values?
I think it's with list, isn't it?
Yeah, why don't you go ahead and make a list that contains 1, 2, 3, and 4.
And it'll print with a little quote thingy. Yeah, I was just looking at that.
Yeah, yep. So it's okay. That's fine. Now, it's not the only way to make lists. We also looked at cons. Right, and we talked about how cons is kind of this inverse operation that's really related to first and rest, actually. Do you remember how to make a list with one element in it? Just say a list with 4 in it, using cons.
Oh, using with just the number 4.
Just the number 4 in it.
Try it like this.
Okay. You do have to quote the empty list. When you use those parentheses right there, remember, this is what I was talking about the special rules. You're not like in a special form here. When Scheme sees an open paren, it thinks you are, and that's what the error is telling you. It's saying probably originally that, which is an illegal empty application. And so what that's saying is you're trying to apply a procedure, but you didn't even tell me what procedure to apply, right? Because that's the rule in Scheme. When you see an open paren, unless it's a special form that's overridden the syntax, you expect to see something after it that can be evaluated, that will evaluate to a procedure that then gets applied to the arguments, right? That rule is just outside of special forms, an ironclad rule.
Right.
Okay.
Yeah, that's it.
Okay, that's exactly right. And what if you wanted to make a list that was 1, 2, 3, 4 using only cons?
Oh, using only cons. So now start with an empty list back there.
Let's think about just the slightly easier case. What happens if you want to? How would you make one that was 3, a list containing 3 and 4?
3 and 4 using cons.
Yeah, using only cons.
Got to do list again.
You can't use list. That's what I'm saying. You're not allowed to use list. Cons should be the only thing that you're using in this line. You can use it more than once, though, and that's kind of the key idea.
Okay, so we're going to go back to an empty one. Wait. Lists. Yeah, I think my inside thing should.
Okay.
Not like the way I'm doing.
So let's think again about types and about the number of things as well, right? Because the number of arguments things take is actually a part of the type of a function. A lot of people don't think about it this way because it doesn't necessarily get made explicit in a ways, but functions have types themselves. And how many arguments a function takes is part of its, we would call it a type signature, but it's part of its type. How many arguments it takes and what the types of those arguments are supposed to be is part of the type of a function. So you can have a function that takes one number and returns another number, and that's kind of its type. It is a function that takes a number and returns a number, right? Mm-hmm. So what is the type of cons as a procedure?
It takes a list and it adds a new item, I'm sure my terminology is wrong, to the beginning of the list.
Well, it actually doesn't have to take a list. We looked at making dotted pairs. You can cons 3 and 4 together. You won't get a list out the other side. You'll get a dotted pair containing 3 and 4. And we haven't talked too much about what dotted pairs are. They are different from lists. We're not going to use them too much right now, although they can be useful. But yeah, let's say, for instance, that you had to always make lists with cons. What would the type of cons be in that case?
I mean, I don't know.
It would be a procedure of 2 arguments, the first of which could be of any type, the second of which had to be a list, and its return type would be list. If we had this special cons that couldn't make dotted pairs, that always just made lists.
Right.
So let's look at what you have highlighted right there, right?
Mm-hmm.
You can look at that and know that it's wrong. Just from its form, just from its superficial form. How many arguments does cons take?
1 argument.
No, cons takes 2 arguments. And this special cons that we're talking about takes whatever you want to make the head of the list, and then it takes the list you want to make it the head of.
Mm-hmm. Okay.
And you also know that the outer cons is wrong too, because you're giving it 3 things, and cons takes 2 things. So again, you can just look at the form of it, and this is what I'm talking about how types can really guide you in terms of knowing what to type, essentially, right? Different use of the word type there.
Right. Well, okay, so if I'm going to do it without a list, without using the special form list.
I don't think list is a special form. I think list is just a procedure.
Oh, okay.
Maybe it's a special form, actually. I'm not sure. Anyway.
Without using the procedure list, that basically means I'm going to be starting with an empty list.
You are. So you're going to have a cons that takes 2 things. Well, no, I mean, it depends on which way you want to look at it, inside out or outside in. I'm going to give you a little bit of a hand with this just to kind of speed things up a little bit. Let's go back to your cons for... Let's go back to this line above, right? What does that produce? That produces a list with 1 element, right?
Mm-hmm.
So that's a list. Cons has to have a list as the last thing in it. You can have another cons here where that's the second argument to it, right? Do you see how that slots in because of the type? You say, okay, this evaluates to a list, therefore it can be, what cons is going to see is whatever it evaluates to, right? Which is going to be a list. So you can then cons something to that list.
Mm-hmm. Right. So that's the interior. That's the one where it's going to evaluate the inside parens first, or the. I'm
gonna just help you out with this. So cons 4, we actually want to make the list 3, 4. So this is actually going to be 3. So just delete what you have highlighted.
Oh, because that would end up with a list of 4, 3.
Right.
Yeah.
Got to get the order correct. And now we want cons 4 to the empty list, but you have extra parens.
I do?
You do.
Oh, because
you're treating this expression cons 4 or whatever as if it evaluated to something that would evaluate to a procedure. Remember this ironclad law: when you see an open paren, the thing that comes after the open paren is a procedure. unless you're in a special form, right? So you've got an open paren, and then after that you have this form that is cons 4 to the empty list. Well, that evaluates to a list containing 4, and you're trying to apply that as if it were a procedure. Do you see what I'm saying?
Yeah. Okay.
Yeah.
Yep. Got it. Right. I don't know why I had that one there. Yeah.
Oh.
So it looks at the highlighted section now. It's basically going to do construct a list with 4, and then it should. Oh wait, I still need one more.
You need one more paren. That's right. Yeah. There you go.
Yeah. Yeah.
Right. And so let's look at this again in terms of symmetry, kind of symmetry with first and rest with car and cooter. Is that what this does is it takes, and this is a pretty good way to kind of remember what cons does. It takes two things and it makes the first thing, it's going to produce a result. In that result, the first thing is going to, the car of the result will be the first thing that you gave to cons, and the cooter of the result, the rest of the result, will be the second thing that you gave to cons. And in fact, if you took first of that result there, you would get a 3. And if you took rest of that result there, you would get a list containing 4, right? But that's what cons 4 to the empty list produces, is a list containing 4.
Right. So this one could have a whole bunch of, I could keep going in that same way.
That's right. So if you wanted to make a list, that was, using only cons, that was a list that contained 1, 2, 3, 4, how would you go about doing that? Yes, exactly. And you might be asking yourself here, well, this seems like a pretty silly way to do this, since I could just type in list 1, 2, 3, 4, right? And, with some merit, if you just wanted to make a list and you actually had all of the things right there to hand to list, that's how you would go about doing it.
Sure.
However, there are cases where you're writing code, and we haven't really looked, and this is going to be the subject of what we do pretty soon, is looking at how you sort of create repeated action, right? Actions that happen over and over and over again, but with something slightly differing each time. And if you might be doing that, and you would need to step by step be building up your list. You would say, okay, the first time that I do this thing, I'm going to put one thing on this list, and then the next time I'm going to extend the list by one more thing, and the next time by one more thing. And so that's why cons actually probably gets used more than list, at least in terms of the types of programming we're going to be doing in the near future. Cons is going to be a bigger deal than list. But okay, so yeah, that kind of brings us to, I'm wondering if I actually want to, do you want to go, can you go till 11 tonight? We got off to kind of a late start, but
right. Yeah.
Okay.
I think I can.
Okay, we have time to get into this then. And so what we're going to get into, I think, I'd like to maybe just look, right, I want to look at a couple more things here. So empty list, it's important to be able to tell if a list is the empty list, right? And so there is a predicate. You remember we talked about predicates?
Yeah, that's the and or the or.
Well, those are actually like Boolean operators, and or.
Okay.
Predicates are procedures. They are in fact functions, generally speaking, but they are procedures that take a single argument and apply some test to it and return either true or false. So a good example of this is we looked at odd, for instance, right? ODD question mark. Try applying that to a number, to an integer.
Right.
Right, because 4 is not odd. And through symmetry...
Pretty weird. It doesn't... Yeah.
What's weird?
I don't know, it's not weird, really. 4 is actually as square as it gets, but...
It's weird that 4 is not odd.
No, I was saying, I was saying 4 is not odd. I'm like, I don't know, it's pretty weird. And then I'm like, no, it's
okay. Yeah, no, it's a pretty, 4 is pretty straight, it's pretty straight laced, pretty prim and proper.
Yeah, it is.
Um,
Even as even numbers go.
even as even numbers go, yeah. Like you get the sense that 2 has a little bit of an adventurous streak there, a little mischief in the eye, but not 4. Right, because if you make 2 a little more square, you get 4. Right.
Yes, indeed.
Exactly. I'm glad we established that.
Now we can retire.
So empty is the predicate to see if a list is empty. So try applying empty to, the empty list. Oh, it's got a question mark at the end of it. It's a predicate. Which is not to say that absolutely every predicate in Scheme must have a question mark at the end of it, but they mostly do. Yeah.
And now if I did so if I'm okay, yeah, that's fine.
Okay. So empty, pretty sure it will blow up if you give it something that isn't a list, right? If you gave it an integer, I'm pretty sure it would just error. But if you gave it a list that had something in it, if you type in empty question mark and then just open paren list 1, 2, 3, 4, for instance, right?
Save it some time.
1, 2, 3, sure, yeah. It's not an empty list. It's a list containing 1, 2, and 3, right?
Yep.
So that's an important one on list. Length, and I think it is spelled out in Scheme. Again, I get my lists and my Pythons and my various things a little bit confused sometimes, but I'm pretty sure you just spell it out. That's not a predicate. It's not asking a true or false question. Well, you can keep the word, just not the question mark.
Of what?
Is that try giving it a list. 1, 2, 3.
Give me the number of items.
Yes. Cool. So that's also, and there are actually a lot of procedures that operate on lists. Scheme is a Lisp. Lisp stands for List Processing Language. So, and in modern Lisp, some of them lists have been downplayed a little bit, but they're still really essential for certain types of things, especially. And we talked about this, especially the fact that Lisp code, Scheme code, is actually made of scheme lists.
Mm-hmm, mm-hmm.
Right? So that will always mean that, at least for certain types of things, lists are very important. So we have the tools now, I think. Do you remember if? Do you remember if, our friend if?
Let me think about it for a second. It doesn't have to have the then so much on the grade, so it's no, I don't really remember.
If usually does have a then, and in fact there's a when instead. So okay. What if does is it conditionally decides to evaluate one branch.
Okay.
Or another. So you can think about the branches as being kind of like bodies, just, a body of code. And you give if has 4 parts to it if you count the it, like if. And if is either a special form or it's defined. Yeah, if is a special form. And we did talk about why it is, and we'll probably mention that again. So if, it has 4 parts. It's got the if itself. The second part of if is something that will evaluate either to false or to something that isn't false, right? We can say it evaluates to false or true, but it can actually have, let's just think about it for the moment as if the second thing evaluates to true or false.
Okay.
And then you have a third thing and a fourth thing, which are both just expression, things that could be evaluated.
Yep.
If the second thing evaluates to true, the first one of those things gets evaluated, and if it evaluates to false, then the second one does. So
it's evaluated or it gets say that again. So there's 1, 2, there's the if, there's the second part of it is
the condition, the test. Yeah.
Uh-huh.
So I'll give you an example here. If you type in if, in fact, let's write a little procedure. Let's write a procedure that that prints whether a number is odd or even. Okay.
Mm-hmm. Um,
So again, you're using the special syntax to define, right?
um,
That defines procedures. Okay. So what's the rule for the special syntax of define? What is the way that that special syntax works? What tells it that you're defining a procedure and binding that procedure to a name?
um,
Yeah.
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 Oh, right. Because if it was just then it would, the next thing after define would actually be the.
Yeah, you'd just be binding something to a symbol. You wouldn't be creating a procedure.
Um, so odd even is going to be the symbol, and
That's
okay.
the symbol the procedure will be bound to the procedure, yeah. And then you do need to have an argument list for it, right? So how many arguments does the procedure take?
Even is it's just going to be one because you just evaluate.
Yeah. Yep. And X is actually a pretty good name for it here. So, and now we have a body. So tell you what, let's define this. Why don't you take this and cut it from there and put it up into the top one? This one we'll hang on to.
Okay, I mean once we're done. Once.
I would do it right now. I would write it right up there. You can hit run to when you need to evaluate it, right? I mean, I guess we'll lose everything that's in the REPL right now, but I don't think we have anything particularly important in the REPL right now. And you need to kind of be willing to lose REPLs in the bracket. I'm sorry?
I'm going to miss it.
Okay. Yeah. One nice thing about this, though, is one of the reasons that I want to move up there is it might be a good idea to backspace over that open paren and hit return.
Oh.
Okay. Which the REPL tends to be a little bit funny, but one of the things is, well, no, don't close your parens. Don't close your parens. That's not legal. Yeah, hit return now.
Oh, okay.
Because writing everything on one line in Scheme gets really hard to read, and you have to keep track of all the parentheses. It gets a lot easier to read this stuff. You'll see what I mean. Do you see how it indented this for you?
Yeah.
You want to keep that indentation. That indentation is telling you something. That is, indentation is telling you what parens are closed. So when you write Lisp code, you typically do not count parens by hand. You look at the indentation, and the indentation tells you if things are what they ought to be. And that takes a little bit of practice. But that's why I want to kind of start moving into like a text buffer so that you start getting that practice and we're not just jamming everything onto one line all the time.
Yeah. Okay, so is it odd or even? So we're going to do if. And if wait, do I have to put another? I'm going to do this, right?
Yep, because you actually want to apply odd to the number. Yep.
If odd and so this will read this as x is odd. Then I'll have to tell it the two things to return, and the first one will be true and the second will be false. I want it to say.
Yeah, I would hit return again here probably. You don't have to though. Right. But no, you're not returning. We're not returning true or false here. We're printing something, but we're printing different things based on whether the number is odd or even. So if the number is odd, print, the number was odd, and if the number is even, print the number was even.
Mm-hmm. Okay. So, and that's just in the order of it, right?
Well,
like the
okay, but you want to print something here, right? So how do you print something?
Oh, I thought that that's what if does for it.
No, if doesn't print things. If evaluates one or the other of these two branches. So you want a branch here that prints something, right?
Doesn't seem right to me.
Okay, well, let's talk about it. What are you thinking that it ought to be doing? I want to just understand what.
If it's so, it's a if if it's a okay. So the the body here of odd is asking whether the x is going to be odd. Okay, so
So odd x, that form there, open paren, odd question mark, x, close paren. You're applying odd to a number. And depending on the number, that entire form is going to, when it gets evaluated, it's going to evaluate to either true or to false because it's a predicate that's being evaluated, and that's all that predicates can evaluate to. So that's the form of if is you have the if, the symbol if. Then you have something that is basically your test, your condition. If that evaluates to true, then the entire if will evaluate the first of the branches that you give it, and it will return the whole if will wind up evaluating to whatever that evaluates to. And then if that second thing evaluates to false, then it's the second branch, and it will evaluate that, and then the whole if will kind of evaluate to that value. And that's kind of long-winded. It'll become clearer what I mean by that in a minute. But so you really just want to do the print here. This is what you want to evaluate. You want to evaluate something that prints something. So print the number was odd, right?
Print what? Print the number was odd?
Just the string, the number was odd. Or x was odd. Well, it's a string, though. It's got to be a string.
Yeah, right. So I just...
That's a symbol. So you need double quotes here.
Right. Whoops.
You don't need to put hyphens in there. You can literally just put spaces in. Once you're in a string, it's just like you're typing English, basically. Close that up, and if you hit return, so that's your first branch, right? Now you need a second branch. This is probably gonna, you want to print the number was even. You do have to end the string as well, just like parens, you delimiters, yeah. And so this is another thing where that color is telling you something, right? Just like indentation tells you something in various things. When the string is dark red, that means you have
yeah. Wasn't done yet.
So now you need to close up all your parens because you're pretty much done here. And as you close them, it will keep highlighting stuff. And yeah, now you can hit return just because it's good to end things with a new line. And now you can hit run. And we haven't been using the top very much, but now we're probably going to switch into using it more. So be a good thing to get kind of comfortable with how it works. You hit run. You're going to lose everything that's in the REPL. We didn't have anything there that we needed to save, though. But what happens is everything in the top gets evaluated. And, whatever side effects doing that causes happen. And so the side effect of define is that it binds something. So if you call odd even on a number,
cool,
and see how that's magenta, right? Sort of purple, whatever that color is, right?
Yeah.
Rather than being blue. That's telling us that we printed it. So that if evaluated to the absence of a value, basically. There was no value from that. Why? Because your print line is what got evaluated, and that print line doesn't evaluate to anything. Okay. So, I mean, this is sort of a dumb procedure, but it kind of follows on from what we've been doing, and we'll probably kind of make this a little bit clearer. Let's write a procedure that returns the value 10 if you pass it an odd number and the value 20 if you pass it an even number. I don't even know what to name this because it's not a very sensible procedure. But there you go.
Yeah.
Okay. It's going to take an argument, though.
Oh, whoops. Yeah. Good number. Right. Just be.
Well, we're not printing anything here.
Oh,
We're just returning 10 or 20.
you don't have to print it.
No. Printing it doesn't return a value. Print just prints. It causes the side effects. We want to actually return the value. We want this function to evaluate to it. Okay, so once again, we're kind of hitting this rule and scheme about open parens. Open paren 10 is just going to blow up, right?
Yeah.
10 itself is a value. 10 is a perfectly legitimate form. Not everything has to, if we want to apply a function to something, we use an open paren to do that. But 10 is just a value all on its own.
Oh, so I don't even need the parens?
That's right.
In there. But I still want to do this?
Yep.
Okay. Right. It definitely, it feels different because it's not on one line anymore.
Yeah.
But I could see that if it was up above, that kind of.
And actually, to be honest with you, I might not have put the 10 and the 20 on their own lines in this case because it is so simple and easy to see already, and because you're not creating a lot of prints. But it's perfectly fine to put them on their own lines too. I don't think I think most people would probably put that all on one line, but they would still have the if on its own line, right? It's pretty much almost all. You very rarely do a define unless it's an extremely simple function where the whole define is on one line. If it's defining a new procedure. Anyway, so you do need to hit run again. Did you hit run?
I did.
You did. Okay, so you should be able to call this now.
Cool.
You can probably hear this, I imagine.
Oh yeah.
Yeah, we have somebody who's a little querulous at the moment. I may give him a little bit of dry food just to keep him quiet in a minute. We'll see how obstreperous he gets. He really likes the dry food, but I have to limit how much of it I give him because his goal in life is to become completely spherical.
Right. Yeah. Not have to walk, just roll.
Exactly. And the thing about it is that I actually think if I never gave him any dry food, he would probably lose some weight, but boy, would he make my life hell for several weeks while he was getting used to it. Because he actually, he could stand to lose a couple pounds, which for a cat is a pretty big deal. If I can stand to lose a couple pounds, it's not a big deal. But
yeah.
For him, that's 15% of his body weight or something. Okay. So, and the reason that I'm kind of doing this as opposed to the upper one, there are some things to learn here from both of these things. Some things that these illustrate about the nature of side effects and the nature of values, right? What things we're evaluating to. So note that, okay, so when we do a define, we create a procedure that has a body, right? Mm-hmm. And when you invoke that procedure, whatever that body evaluates to is what the procedure returns, right?
Mm-hmm.
Okay. And then we've also said if gets these two branches, and it's going to evaluate one branch or the other branch, and the entire if statement will evaluate to whatever the value of the branch that it evaluated was. It's kind of a hard thing to put simply, but do you see what I'm saying by that?
Well, I mean, okay, let me look at this here for a second. It's odd.
So if you type now down at the REPL, because this isn't something we want to keep, right? This is something we just want to invoke. Try just typing in an if with the same form as that odd, but just like give it 3, right? Because this isn't, we're not going to have an argument, a formal parameter of this. We're just going to, just say if odd 3, and we know what the answer is here, but if odd 3, close the paren, 10, well, you do have to give it its branches, right? Yeah, 10, 20, yeah, and close up your parens. Do that.
Mm-hmm.
Okay. So that whole if got evaluated. That is a form. It got evaluated. The whole thing evaluated to 10. Well, why did the whole thing evaluate to 10? Well, it looked at the odd 3, and it said, okay, I'm going to just evaluate the second thing that I have here, my second branch, which could be as simple as a value. And I'm going to say that the whole if evaluates to whatever that evaluates to, right?
Okay.
Is that clear?
I think so. Uh, no, maybe it's not. The whole if evaluates to the second form, which is in this case is the odd question mark 3.
The if does not evaluate to that. It evaluates it as part of its operation. It evaluates and says, is this true or false? If it's true, then it evaluates the second, the third thing, the second branch, the first branch that it's given out of the two branches.
Yep.
It evaluates that, and then what the if returns is kind of the wrong word here because it's a special form, but like the whole if evaluates to whatever that branch evaluates to. So when the if evaluates one of the branches, the whole if itself has to evaluate to some value as well, right?
Gotcha.
Right? You typed in a value at the rep, you typed in something at the REPL, and that was an if. So that if has to evaluate to something, right? Remember, you note that like when we do a define, for instance, define just evaluates to the absence of a value, right? When you do a define, nothing gets printed at the REPL, right?
Okay.
So something definitely is getting evaluated in there, et cetera. Whereas when you do a lambda, the lambda itself evaluates to the procedure that it creates, right? Things evaluate to things. And so the if evaluates to the value of whatever the branch that it evaluates, it takes that value, what that branch evaluates to, and then the entire if evaluates to that is treated as evaluating that value.
Okay.
Exactly.
Yeah.
Same thing with the other one. Let's note something really important here. It never evaluates the branch that it doesn't evaluate. It never evaluates it. So this is why if can't be a function. We talked about this a couple of times ago. The if could not be a function. It could not be a procedure. You could not write the procedure if. And the reason is procedures always evaluate both their things. So if you tried to write a procedure for if, you can come pretty close to it. And in fact, if you were doing something like this with just like pure values, 10 and 20, something like this, it would work to your eye, right? It would appear to work. It would do what you intended it to do. But look at that if where we have those two print lines, right? It's very, very clear that the second one, when you pass that 3, that the second one did not get evaluated, because if you evaluate a print line, something gets printed.
Gotcha.
So if you passed print line the number was odd and print line the number was even, if you passed those as two arguments to any procedure, you would see both things get printed. Right? Do you see what I mean?
So, but does that mean that? Well, let me try this then. Let me see. What did we call it? It's the odd even one. Just let me do a little thing. It's still only going to print one thing, huh? Even if it's the second. It'll give me the number was even. Oh no, it's 20. Oh, because we got a new. No.
Yeah. So.
That's not what I meant to do.
Yeah, you typed in the 10, even 20.
Yeah.
Yeah.
So.
Okay. So if that were a procedure, if we're a procedure, no matter what else, both those prints would be printed because the arguments to procedures get evaluated before the procedure is even invoked, right?
Yeah.
So they would both get evaluated, and when you evaluate a print, it prints. So this is how you know if is a special form, right? If it has to be a special form.
Yeah. Got it.
We saw that this is also true of like and or, for instance, right? That as soon as it hits something that allows it to say, okay, this is true, right? Then it will return that thing. So if you give and like 6 things, as soon as it hits one of them that's false, it's going to return that. And it's just going to return false, right? With or, though, as soon as it hits something that's true, it's going to return whatever that value was. And we talked a little bit about truthiness. Do you remember our conversation about truthiness?
Well, I was listening to that on the drive home, and I kind of got it, but I got to say that truthiness is a little bit hard.
It's actually really, really simple, which is that when you're in a Boolean context, okay, That is to say, when you're looking for a true false value, like if, that first thing that you're passing to if, that's a Boolean context. You're looking for something that's true or false, right?
Yep.
You can still use other values there that aren't true or false. They get treated as if they were true or false according to a rule. And that rule is pretty much, are there any exceptions? If it's false, that's false. If it's basically anything else, it's true. Everything else is true in Scheme, is truthy, right?
Okay.
So most of what we're going to be dealing with right now is actually true predicates. So we're mostly actually going to be giving if true or false. But if can also, take other things. Or though does not have to just be a bunch of like trues and falses. You can apply or to just a whole bunch of things, and basically unless they're all false, it's going to return whatever they are. They don't have to be true.
Okay.
So if you type in like open paren or sharp F, we'll give it a false just to give it a false sense of security. And then space 3, and then space 6, and then space false again, right? Wow, he's really being loud. I'm going to give him a little bit of dry food. I'll be back in 1 second.
Cool.
Okay, I'm back. Right? So it gave you back the 3, right? The or was like, okay, let's look at this first thing. It's a false, right? And you remember basically how or works, right? Are you there?
Yeah, you just need one thing to be false.
You just need one thing to be true. If any of the things are true, then it's like fine, right?
Okay. Yeah, I have it back. And is the one you've.
And needs everything to be true.
Mm-hmm.
And needs everything to be true, or needs just one thing to be true.
Yeah. Okay.
So, but you can see here that it didn't return true, right? It returned the first truthy value that it came to.
Mm.
And most of the time you don't use, most of the time you don't really use that. You're using or in a Boolean context. So you just care that it evaluates to something truthy, because you can use an if, for instance. You can use an or like that as the body, as the test in an if, right?
Mm.
So given that it's returning the 3, it's very important that the if treat that as true, right?
Mm-hmm.
Okay. So we're going to move on to something now that is often considered quite difficult by people when they first encounter it. It's a funny thing. Once you get it and you see how it works, there's this kind of penny drop moment that people tend to have about this, where the penny drops for them and they go, oh, okay, this isn't as hard as I thought it was, right? This makes total sense. It does tend to give people difficulty sometimes. And I don't really want to I don't want to intimidate you by pointing this out, but I will just say this is something that people tend to find difficult at first. Okay.
Mm-hmm.
And I'm kind of thinking about the best good example of this. And so there's a really classic example of this, actually, which is factorial. You see factorial a lot. Do you know what the factorial of a number is? Are you familiar with factorial?
I remember that.
Okay, a factorial, like the factorial of 5 is 5 times 4 times 3 times 2 times 1.
Gotcha.
Okay. And it actually turns out that factorials come up in a number of places in the real world. Factorials, actually have real applications. And there's a really fast way to calculate factorials. So what we're going to do here is not actually a sensible way to calculate factorials. So one of the things that's kind of interesting about factorial, we're just going to write it out, and I will help you write it out because it's what we're going to use as our example to dissect. So I'm not going to expect you to write it out because, you You don't even
Haven't
know what
done.
we're really trying to get at here yet. Let's just write it out. So if you go up into the top and start defining a procedure that takes a single argument and call it factorial. Okay, it's the special syntax for define.
Oops, I forgot that.
Yeah. Okay, and we're going to make some assumptions here, right? We're not going to bother. It doesn't, for instance, make sense to take the factorial of a negative number. Right? That's just something that doesn't make sense. So we're going to assume that somebody's being good and is going to actually pass us. We're not going to check for this. I'm going to say the function that we're going to write, it would not be safe to pass it a negative number. Bad things would kind of happen if you did. Okay, so... Well, actually, let's write it a little... Well, no, okay. We'll write it this way. So it is convenient for a variety of reasons to define the factorial of 0 as 1. To say factorial 0 is 1. Okay. It's just a convenient thing to define it as. So...
Yeah, otherwise it would return 0 every time. I mean, 0, yeah.
Yeah. So here, why don't you type in this? So we're going to have an if here, and we're going to say if x equals 0. So, okay, the way that you do equality, I'm sort of speaking English here. I'm assuming that you will sort of parenthesize it. You need a paren here, and then you need an equal sign.
Gotcha, right.
And then an x, and then a 0. And close up your condition. And so we've already basically said that we know what this is, right? So what are we going to return? What are we going to return if x is 0? Yeah, but put it on its own line. We're going to want this to be multi-line. Yeah. Now hit return again. And now open up a paren. And just think about this for a second. We're going to multiply x by the result of calling factorial with x minus 1.
No.
Yeah.
Whoops.
Yep.
Oh, I don't have to put minus before I factorial? No.
No. We're going to call factorial, and what we're going to pass factorial is x minus 1. Okay, you need to open parens. Again, because...
Oh, yeah, I got it now.
Yeah. X minus 1. So minus...
Okay.
Yeah. And, yeah. And note that unlike plus, right, order does matter here, but I'm pretty sure that's correct. Yeah, so...
Yeah. Yeah.
And now close up all your parens.
That does it just from the same one. Okay.
Yeah, and now run this.
I got it. Do I have to return there?
It's a good practice to do that. Files should always end in a new line. That should always be the last thing in a text file. So, and you may want to save this eventually, in which case it will be a text file.
Okay, cool.
Okay, so try calling factorial with 5. Let's see if we got this right. That'd be pretty embarrassing if we didn't.
Was it like 120?
Yeah. Okay. So let's take a look at what happened here, actually, right? What happened here? How did this work? Because this seems a little like magic, right?
Mm-hmm. I mean, it must. Because factorial, is just a name bound to this overall procedure.
Right.
So let's see here, and the x, if x. Wait a second. Why is that 0 in there? So it says if equals x 0.
That is if x is equal to 0. That's our test. Is x equal to 0?
Mm-hmm.
And if x is equal to 0, we want to just have the if evaluate to a 1. We want to return a 1 there.
Oh yeah, under if okay.
That determines which branch of the if we're calling.
Okay, well let me look at this other thing down here. X minus 1. So 5 multiply. I don't know. I can't figure it out.
Okay, let's talk about what happened here. So here's a question for you. How many times did factorial just get called?
Well, it seems just once.
Actually, it got called 6 times when you executed that line. And so that's what's kind of interesting about this. Note that we are actually calling factorial from within factorial.
Mm-hmm.
Okay? So if you call factorial with 0, we don't ever call factorial, which we eventually did, by the way, in that. And we'll get to that. But if you call factorial with 0, the if looks at it, it says, this is equal to 0, so I'm going to return 1. Okay? And you're done. And that function invocation of factorial is over. However, if x is not 0, let's say that x is 5, okay? Then we're going to execute the second branch of the if. And whatever that evaluates to is what that whole if is going to evaluate to. And that means what this invocation of factorial is going to evaluate to, right?
Yeah. So, yep.
So we're going to multiply x by something. That's the value that we're going to return. What are we going to multiply it by? The result of calling factorial again. But we're going to call factorial with x minus 1. So if x is 5, what we're going to do is we're going to multiply 5 by the result of calling factorial with 4.
Yeah.
Right? Because that's 5 minus 1.
But how does it know to loop back?
It doesn't have to know to loop back. It's just calling factorial. It's just invoking the function. Right? It just invokes the function. Well, what does the function do? It takes this number, x, and it compares it to 0. What's x?
5.
It's 4 this time. Okay? We have another invocation of the function, and that invocation of the function has its own environment. And this is what's a little tricky to understand about it, is this is a separate invocation of the function. This is the function getting invoked a second time with the value 4 rather than the value 5. Okay?
Okay, I can see how we taper it down. It's going to count if it keeps subtracting by 1 each time, with the x minus 1, then it'll get down to 0 and it'll return a 1 there.
And it will return a 1 there. And then it has to come back up through these function invocations, right? So it can't do any of the multiplications until it's bottomed out, because it has to know what both numbers are in order to do a multiplication, right?
Oh. Yeah.
So.
What? Well, no, it knows. I thought it knows that it's 5 because that's what you gave it.
It knows x is 5.
Yeah.
But does it know what the second? It's got to multiply x by something, right?
Yeah.
So
gotcha.
Let me ask you something. What is x in the very first invocation of the function that we called? What is x actually being multiplied by?
By the whatever factor. I don't know, by that thing up here.
Well, by the factorial of 4, which happens to be 24.
20. Yeah.
No, 24.
5 times 4.
5 times 4 is 20. But we're not multiplying 5 by 4. We're multiplying 5 by the factorial of 4. Right? Note that we got 120. What's 5 times 20?
100.
Okay. What's 5 times 24?
Yeah, 120.
Right. So it definitely multiplied 5 by 24.
Oh, overall. So okay.
That's what I'm saying. I mean, in that first invocation, that first invocation of the function, factorial, when we called it, it just multiplied x by something. That's all that happened. The second branch of the if executed, right? And it said, we're going to multiply x by some value here, right? That value was 24. We know that. We can look at it. It's 5 times 24. It's 120, right?
Okay.
24 is the factorial of 4, right?
Gotcha.
So there's two ways to think about recursion. And one of them is to think just in terms of definitions. So a pretty easy way to define the factorial of a number is the factorial of a number is that number times the factorial of a number one smaller than it, right?
Mm-hmm.
That's a perfectly fine definition of factorial, as long as we kind of know what the factorial of 0 is. It's pretty important that we know what the factorial of 0 is, because it's got to stop at some point.
Wait, but why doesn't it just and I mean, if you're just counting down, then why couldn't you just keep counting down into the negative numbers? I guess zero being 1 starts you back up or something. I don't know.
It doesn't start you back up. It's like we're done. So here's the thing. We're defining something in terms of itself, which is very circular, right? Very circular kind of thing, which is part of what makes it a little hard to think about this sometimes. So we're defining factorial. We can say that what is the definition of factorial, of the factorial of a number? Oh, well, the factorial of a number is just that number times the factorial of a number one less than it, right?
Yeah.
So that's almost an adequate definition of this, except that, so first of all, we have to say factorial is only defined for non-negative integers.
Yeah.
It's only defined for them. Factorial is undefined for negative integers. And so we can have this definition of factorial that says, well, if a number is 0, then its factorial is 1. If a number is not 0, and assuming it's in, the non-negative integers where it's defined, if it's something it's defined for, then it is the factorial of a number 1 less than it. Okay? So that's the way... Mm-hmm. It is right. It is itself multiplied by the factorial of the number 1 less than that. And that's a definition. And most of the time when you're writing recursive functions, you want to think about definitions rather than what the computer is actually doing. But in order to kind of understand things at first, we have to think about what the computer is actually doing. So I just kind of want to point this out as a little bit of a warning about this, which is that in the long run, you do not want to be thinking about the function calls, and you do not want to be thinking about what people often refer to as the stack, although it's a misnomer in Racket to call it the stack. But you do not want to be thinking about the environment of all of these invocations of the functions and what they're getting passed as arguments and what their environment was and just all of this stuff. But it's important when you're understanding recursion. It is kind of important to actually at least think through what the computer did. Okay? So that's kind of what I want to do is think this through with you. Mm-hmm. So we called factorial with 5. And the second branch of our if is what got evaluated. Right? And that's what the whole invocation, that top level invocation, is going to itself evaluate to, is whatever that second branch evaluates to. Right?
Yep.
Okay. Because that's what the if evaluates to. And that's, just like up above when we did that odd 10, even 10 of x, the whole procedure evaluated to either 10 or 20, depending on what you passed it. Well, it did that because if you have an if, and that's the only thing in your body, that what does your body evaluate to? Well, whatever your if evaluates to. What does an if evaluate to? An if evaluates to the value, to whatever the branch that it evaluates to. There's a lot of uses of the word evaluate, but did you follow all of those uses?
Yeah, I think so. I mean, this is one of those things of to the level of being able to grasp it and actually verbalize it back. I think the fact that I stumble over verbalizing means I'm grasping it to the extent that I can verbalize it in a way. But I guess the way that I say it is, or thinking or shorthanding it, it feels like the moment is just, the if is evaluating to which branch is the procedure is evaluating to is picking as the not picking because that makes it sound arbitrary, but
well, you can pick things non-arbitrarily. I often do. But yeah. It's just kind of important to understand the rules of evaluation here, right? This is all getting evaluated according to a set of rules.
Mm-hmm.
Right? And so the rule is what does an if evaluate to? it's the branch that, it's whatever the branch that it evaluates. It picks one of those branches. It evaluates that branch. It takes that value, and the entire if evaluates to that value, right?
Yeah.
Okay. And then what does a procedure evaluate to, right? Well, it evaluates to whatever its body evaluates to. And assuming that it's like a single form body, it's like that form evaluates to something, the procedure evaluates to that. The whole procedure, when you invoke it, evaluates to that as well.
Mm-hmm.
Okay.
Mm-hmm.
But it's kind of important here that we keep very, we're very kind of strict about thinking about these evaluation rules and being very literal about them, as we've talked about before. We want to just be very literal about what these rules are. So we've talked about how, procedures, when they're invoked, they have an environment, right? And we looked at let. It's been a little while since we looked at let, right? But do you remember let, our friend let?
Yeah.
Let allowed you to establish some bindings and then evaluate something with some bindings established that weren't at the top level, right? Once the let is over, those values kind of go away. They're just in let's environment. It creates an environment for you. So procedures are like that too. And in fact, we talked about this a little bit. Let can be implemented in terms of lambda, actually. Because that's how names get, if we ignore top level bindings at the moment, that's kind of how names get bound to values, is lambda. Lambda, it's largely what lambda exists to do, is create an environment in which we have names that are bound to some values, right? I mean, that's why it's useful, because when we write a procedure that's like, well, let's add, that takes x and adds 10 to it and multiplies that by 7, right?
Mm-hmm.
If you already knew what x was, there would be no reason to write the procedure. You would just write it out. If you knew x was 3, you would, multiply 3 by 7. I may be getting this backwards from how I said it, but whatever. Multiply 3 by 7. Or like sum of squares, just so that we have something that we really know what it is, right? Sum of squares takes like two numbers, it squares them each, and it sums up those values, right? And it returns that. So if you know what those two values are, if you have a 6 and an 8, for instance, you don't need to have a procedure to do that. You can just write it out. You can write out plus, times 6, 6, times 8, 8. You just write it out. The thing is, if you don't know what they are ahead of time, you want to have a general purpose procedure that says, well, I want to, square these two things and then add those up together. When you write out that body, you need to have a way of referring to like the first thing and the second thing. Right? And so if you write a procedure and its argument list is like X, Y, you say, okay, these are going to be names and I'm going to bind them to these values so that I can write out this body and I can refer to these things in that body. Right? I mean, that's really what we're doing with lambda. That's why we need lambdas, right? Is so that we can refer to things that we don't know the value of yet.
Yeah. Gotcha.
So within the body of a procedure, and this is getting into the implementation details a little bit, and most of the time we don't want to think about implementation details when we're not actually implementing programming languages, but sometimes it can be useful too. And so we say that within the body of a procedure, it has an environment there, right? And that environment has some name bindings in it, right? And we've talked about how environments can nest, right? And we've seen how when you do that, they can shadow bindings that exist in the outermost scope, right? In the outermost scope, if you have something defined, they can just shadow that value. But it's specific not only to that procedure, but to that invocation of the procedure, right?
To that invocation
of the procedure. When you invoke the procedure with 6, the X gets bound to 6, right? But then you can invoke the procedure again with 10, and the X gets bound to 10. Each invocation of the procedure has its own environment. It creates an environment when you invoke it. It does its bindings, then it evaluates the body. Okay. Okay. So now when we come back down here to factorial and we call it with 5, we say, okay, we create an environment and we bind the symbol X to the value 5 in that environment. We say we create that binding. So now we're going to evaluate the body. So we get down here, we have a multiplication. So we're like, okay, we're going to multiply 5 by, something. What is that something? Well, it's called a factorial, right? So we call factorial again. And what do we call it with? Well, we're subtracting x1 from x, and we have that binding for x. That's 5. So we know that it's 4. So we call factorial again. And note that we have not done the multiplication of 5 times anything yet, because we don't know what the answer is. It's 24, right, as we recently established. That's what it's going to be. But we don't know that yet because we haven't actually evaluated factorial, right?
So 5 is still just sitting there.
The 5's just sitting there waiting to be evaluated. The 5 has already pretty much been evaluated. That's probably the first thing that got evaluated, times. So now it's times 5 something, okay? But we can't actually do that multiplication yet because we don't know what the something is. The something is going to be the result of evaluating factorial. So we call factorial and we create a completely new environment. And we bind x to whatever we passed in, which was 4 in this case, right?
Yeah.
So we go down into this if, and we get to the second branch again. And we say, okay, we're going to multiply 4 by something. We're going to return that as our total value, 4 by something. We don't know what that something is yet, but we know that it's the result of calling factorial with 3. Are you with me so far?
Yeah.
Okay.
Well, I am. I just I can't really, I don't know how it's going back up to the if again.
It's called, what happens when you call factorial? What's the first thing that happens when you call factorial? When you invoke factorial? It runs its code. So this is a totally new call to factorial. It's not jumping back up to that, it is kind of the same code in a sense, right? But you're starting over. You're actually executing factorial again. It is a new invocation of the function.
But it's now down all inside of that. It still kind of starts where the
you're stacking up some things that you still have to do. You still have to do all your multiplications. Note that no multiplication has happened yet.
Yeah.
Okay. We haven't been able to multiply anything yet because we haven't.
We're in this part. And it keeps looping back to, it already did. It did this little piece.
Except that it hasn't done the multiplication yet because we didn't know what the multiplication was. So let's go back to the beginning and look at it again from the point of view of when we first called it with 5, right?
Mm-hmm.
So we hit that second branch and we say it's going to be 5 times something, times 5 as the syntax is written, right? Something. It is sitting there waiting to do that multiplication because it does not know how to do it yet because it has to know what that second thing is that it's trying to multiply, right? So it calls factorial again. And the way that it knows to start from the if is where does factorial always start from?
Yeah.
It's
defined.
Right?
Defined up here.
Yeah, that's just what factorial does. That's what factorial's body is. It's this if statement, right?
So it's a whole new thing of this without the 5 in it, where x is back to being x, and now we know
x is 4.
Yeah.
We're passing it negative x1, so it's a new environment and a new set of bindings because it's a new invocation of the function.
It's
of
this
the procedure.
Here.
Right. So there's a new one, and they're kind of nesting inside themselves.
Mm-hmm.
And let's do this. So we get into this if again, and it's 4. So it's not 0. So we know we're going to execute the second branch again. So we get down there, and we're going to say, okay, times 4 factorial of that. Okay. And we're going to, that's going to be 3. So we're going to invoke factorial with 3.
Yeah.
And so it's gonna, again, execute that if, because that's what factorial does. That's where factorial begins, is by doing this if. And it says, okay, 3 is not 0. So once again, we're going to do the second branch. And we get down there and we're like, okay, we're going to multiply 3 by something. Well, what is that thing? We don't know yet, but it's going to be the result of calling factorial with 2.
Mm-hmm.
So we call factorial with 2. Again, we hit the second branch because 2 is not 0. Again, we're like, okay, so it's going to be 2 times something. What is that thing? We don't know yet. So note, we still have not performed a single multiplication, right?
Yeah.
They're all just sitting there waiting to be done. So now we're going to call factorial with 1. And we get in here. Is 1 0? It's not. So we're going to execute the second branch. And we're going to say the result of multiplying 1 by something. And what is that thing? Well, it's the factorial of 0. So we go back, factorial gets called. We look at the if, we say is 0 0, and we say, 0 is 0. Okay. So we're going to return a 1. So now we have a whole line of multiplications waiting to happen, right? And so the most recent one happens first.
But wait, why does it stop there though? That's what I don't understand.
Because you don't call factorial again, right? Only the first branch of the if gets executed.
Yeah, it takes the first branch on that one because you had
the first branch. So it just evaluates to 1. There's no call of factorial there. It doesn't do anything with the second branch. Okay.
Yeah.
So it goes, here's a 1, and that's fine. So now we're done. We're done. We have bottomed out, essentially. So we go back, and we were waiting to multiply 1 by something. Well, that something turns out to be 1. We know that. So it's 1 times 1. It's 1. We were waiting to multiply 2 times something, and now we know what that something is. 2 times 1.
Because that was the result of the first nested multiplication.
Yeah,
process.
the most recent one. It's just, it does them kind of in the reverse order that it stacked them up, right? And then it's like, okay, 2 times 1. And then we go, then we're done with that invocation. That invocation is over, right? And
it's return that result.
It returned that result. And so, here we are, and we were waiting to multiply 3 by something. And now we know what that something was. That something is a 2. So we multiply that out, and we go, that's 6. And now we had another multiplication waiting, and that was 4 times something. And that something is 6. So we get 24. And then we were like waiting to multiply 5 by something. And we say, 5 times 24, and we get 120. And that's what gets returned, and you're done.
Yep.
So it's actually pretty straightforward.
Yeah.
However, it
was that piece I was like, okay, how's it going to stop?
Well, that's a very important piece. And we call that the base case. And when people are starting to write factorial functions, they often write, recursive functions, because what we are talking about here is recursion. Okay. This is the name of this technique. And recursion can get significantly more complicated than this, but this is sort of the first step with recursion. And so when people start writing recursive functions, it is fairly common for them to forget to write base cases. And if you forget to write a base case, your function never terminates. Eventually you run out of memory, right? And you have to kill your instance of scheme and start a new one because it's dead. It's dead. It's just running forever, right? So you want to avoid writing recursive functions that do not have base cases. You also want to make sure, because this is really, really important, that every invocation of the function gets you a step closer to the base case.
Right.
Yeah,
because you get, rather than going in the other direction. Yeah,
right.
Man,
if you forgot to do the subtraction there,
yeah.
If you called that with factorial of x instead of factorial of x minus 1, again, it would run forever because it would just keep calling it with 5, and it would keep taking the second branch. And it'd be like, I'm going to call factorial again with 5. Be like, call the second branch. I'm going to call factorial again with 5. It would just go forever.
Yeah.
So,
well, you could do like plus x1, and if x, how would you do that? And instead of putting if x equals 0, return 1. If you said if x equals whatever, 20, return.
Yeah. That could be a base case. However, you would need to be very, very sure that it was never, ever, ever called with something that was greater than 20.
Right. Okay.
Because then it would go forever. And so what you might actually say was something like, you might either actually throw an error, you might put a safeguard into it. And we could do that too in this. We could, if we wanted to be sure, because this would run forever if you passed it a negative integer. Right? So, and in fact, it would be legal to pass this with like a floating point number. You have to pass this a floating point number, like 2.5. This would also run forever if you passed it 2.5.
Oh yeah, because you subtract by 1 and you'd end up at like 0.05, and then you swerve into negative numbers.
And then you'd wind up with negative 0.5. And
then
negative 1.5, it would go forever. So, one of the things about this is that when you write this kind of function in real life, you are often going to, like, one of the things about it is that your code should never be able to enter an infinite loop when you write real production code. Like, that should not be possible even if you are given bad data. And that's very important when you are writing real code, right? Is that you have some checks in there that whenever you write something that looks like it could be an infinite loop, you know for sure that no matter what data you get given, it's not actually going to run forever, right? I have a very embarrassing story related to that, which maybe I'll tell you sometime.
Wait, so what's it called again? It's base what?
This is your base case.
Base case. Okay.
Yeah, this is your base case. And so recursive functions have to have one. And every invocation of the function has to get you closer to it, right? If you have an invocation of the function that doesn't get you closer to it, then your function's going to run forever.
Okay.
So let's try something. And I mean, I think we're probably going to have to write a couple of these, mostly with me writing them, before we get to the point where it makes sense for you to try your hand at it. But like, let's just see if you have sort of an idea of. You remember there was that function called length of lists. How do you think you would go about writing that using a recursive function?
Well, I guess I'm trying to think about like. So this is a recursive multiplication function that we just wrote with factorial. Would that be accurate way of
I guess so. It's a recursive function. It happens to involve that calculates a factorial. It happens to involve multiplication just because factorial involves multiplication. That's kind of the definition of factorial, right? It's 5 times 4. It's a number times, it's 5 times 4 times 3 times 2 times 1 if it's 5, right?
So factorial in this case is not just the name of this function; it's the actual.
Right. We happen to name it. We could have named it anything, right? Like in scheme, it doesn't matter what we named it, but we named it factorial because that's what it does. Right. We could have named it Tom, Dick, and Harry, and it would still have done the same thing.
I guess I'm just trying to it makes sense to me, like recursion as well, maybe it doesn't completely. I mean, it definitely factorial makes sense, pretty straightforward.
Yeah, you'll need to see it play itself out in a couple of other contexts before it.
Right.
There's some wrinkles to this, but
a recursion is basically a kind of repeating, either descending or ascending, like in regular increment or defined increment, right? Yeah, regular. I don't know.
It
I'm not
doesn't
sure.
necessarily have to do that. Those things don't necessarily have to happen. What makes this recursive? So there's a couple of different ways of thinking about recursion. You can think about recursion just from a mathematical point of view, and recursion from the mathematical point of view is when you define something in terms of itself. So we made a recursive definition of factorial because our definition of factorial is that the factorial of a number is 1 if that number is 0, and that number times the factorial, if it's not 0, then it's that number times the factorial of that number minus 1. Which, is pretty much what we wrote as code, too. And that's kind of the nice thing about it, these mathematical definitions.
Yeah.
So from a mathematical point of view, it's just the fact that we defined it in terms of itself that matters, that makes it a recursive definition. From a programming point of view, it's a recursive function, and we'll get into this a little bit. We'll talk about this in a little while. The difference, this is not just a recursive function. It is it performs a recursive procedure as well. What it did was recursive, and that's not always true of. This is some stuff I don't quite want to get into yet, but a really important part of this, the thing that kind of makes this different from any other procedure that we've written, is that this procedure calls itself within its own body, so it reinvokes itself again. Right? So that's a pretty key thing to writing these recursive procedures is now you can even have, and again, we won't get into this much, you can have recursive, like mutually recursive procedures. You can have a procedure A that calls procedure B and procedure B calls procedure A.
Yeah. But again, you have something else in there. You're gonna.
There's got to be something that breaks that cycle. Eventually, things have to be getting closer to a base case. And there's some very, very interesting mutually recursive procedures. When you are writing parsers, things that actually can take in something like a programming language and figure out how to evaluate that programming language, it's very common to write something called a parser. That is part of the step of doing that. And parsing often involves mutually recursive functions. That's one way to sort of parse. But we won't deal with that yet. But it's just important to understand that's also recursion. So in that case, neither procedure calls itself, but it calls another function that calls it. Right? That's also recursive.
Got it. Right.
So I also mentioned that there's two ways of thinking about recursive procedures, and that one of them is to be preferred over the other most of the time. And one of the ways of thinking about it is just definitionally. You think about the recursive definition of something, and they're almost inside out of each other, right? They're almost inside out. Because when we think about what the computer does, you have to kind of think about when it gets to the base case first and sort of work your way back, But when you think about the definition, you just sort of think about it almost the other way around. So let's think about this. Can you define the length of a list in terms of the length of lists?
In terms of the length of lists, this is attempting to do a recursive.
We want a recursive definition that tells us like how many items there are in a list, right? Because we don't really have a good definition for length. You say, oh, it's the number of items in a list. Okay, but like we kind of want that. That's not a definition that a computer can deal with, right? That's begging the question, right? That's and recursion is not begging the question, even though it kind of looks like it is, right?
Let's think.
And think about it this way. You can do this in terms of car and cooter or first and rest. First and rest are important here.
Okay.
Particularly rest. First isn't as much.
Okay.
Well, so let's think about another thing, because sometimes it really helps to think about base cases. If we're talking about the lengths of lists, what's probably our base case?
Empty list.
The empty list. And what is the length of the empty list?
0 or no value.
0. No, it's definitely 0. It's not no value. It's 0.
Okay. Yeah. 0, right? Because it's 0 items or whatever.
Length has to return a number. Length, if length successfully evaluates to something, it evaluates to a number. For sure.
Mm-hmm.
Okay.
Mm-hmm. Yeah. So
we kind of have that part of our definition. We have the base case. Okay. The length of a list is, if the list is the empty list, then the length is 0. So what if the list is not the empty list?
So
how would you, if you had to write down an expression for it that involved the rest of the list, what would that expression be? How can you define the length of a list, assuming that it's not the empty list? How can you define the length of the list in terms of the rest of the list?
Well, it would be like the empty list.
Well, we're not dealing with the empty list here. We're talking about a full list, right? We're talking about a list, say the list 5, 4, 3, 2, 1. Okay. What's the rest of that list?
4, 3, 2, 1.
Okay. How would you define the length of the list in terms of the rest of the list?
Oh, I would do the rest plus 1.
Well, the length of the rest plus 1.
Okay.
Okay.
Yeah.
That's an important step. That is the recursive step. Okay. So that's actually a perfectly suitable definition of the length of a list. The length of a list is if the list is the empty list, then the length of a list is 0. If the length of the list is not an empty list, then the length of the list is 1 plus the length of the rest of the list.
Mm-hmm.
So can you write that procedure? Because that's a perfectly workable definition to write a recursive procedure. Can you write, you don't want to name it length because there's already a length. We don't want to overwrite the existing length, but you could name it my length.
Do you think I should try this up?
Yeah, try it up in the top.
Now, would I just say?
Well, remember, we introduced a predicate before. So we want to test for the empty list here, right? We introduced a predicate named empty. So you still do need an if. Yep. I mean, you still need the if, right? But what's your base case?
Empty list.
That the list is empty. How do you tell if something is an empty list?
Yeah, right. You can't just.
That's not going to work because, in fact, the empty list evaluates to true. The empty list is truthy. But also, that's not going to change, and this has to be something this has to involve the actual x, right? Because you're actually testing to see if it's x. I actually wouldn't name that x, by the way. I would name it LST. X is a good variable name for numbers. Yeah, again, because we don't want to name it list because that symbol list is already bound to something, right? We don't want to reuse it, but LST is a pretty common way to refer to lists in schemes. So we'll name it that. So we want to test to see if that list is empty. How do we test to see if a list is empty?
How do we test to see if the list is empty? We check its first.
No, we don't check its first. If it's an empty list and you try to check its first, it will be an error. If you call first on the empty list, that's an error. No, remember we had that predicate empty that we introduced before, EMTY question mark, and then a list?
Oh, no, I don't.
Okay. We looked at it about an hour ago. And this is why, because I knew this was coming up. But, yeah. I know it's a lot of stuff going by. It's pretty easy to lose bits of it. But this is how you check to see if a list is empty. You just say empty question mark list. So, if...
List. Okay, right.
You can try it out down at the REPL. If you're a little unsure of how things work, there's one of the nice things about working up top and in the REPL is you can always just be like, how does empty work? And just jump down into the REPL and execute it if you are curious about it. Okay.
Right.
So if the list is empty, if that returns true, which it will if it's an empty list, we want to return what?
Zero.
Zero. That's exactly right. That's the length of the empty list, right? Because note that that's what this whole invocation is going to, what we're trying to do is figure out the length of the list.
Yes, sir.
This whole thing is going to evaluate to it, meaning the function will evaluate to it. And indeed, the whole thing will evaluate to zero, which is what we want. If it's the empty list, right? So now we need a second branch. And that second branch is basically going to just be writing out the definition we just came up with, the other half of that definition.
Which is so it's going to be the length. Oh, okay, right. It's going to be the remainder.
So what was that definition?
It was basically the rest plus the first.
It was one. It was one plus the length of the rest of the list, right?
Length, yes. Okay, good. So let's see. Let's do.
Okay. Remember again, you do need spaces.
This one.
So you're going to add two things together, and you know what one of those things is already for sure. One of them is easy. Let's get the easy one out of the way, right? We're adding one to something, right? So let's get the one in there, yeah. So now all you have to do is think about the thing that you need to add the one to.
Isn't it the recurrent length list?
Mm-hmm.
Same thing. Oh, wait.
Well, this is pretty close, but is that getting you closer to your base case? So what was the definition again?
Yeah, it's the remainder, or the, what do you call it again? The rest.
The rest.
the rest. And how do we do that again? That's just isn't that it?
Oop, oop. No. You want to pass recur length the rest of the list.
You want to pass?
Yeah, you can't call rest with recur length. Recur length is a procedure. Rest can't be applied to recur length. Okay, you want to call recur length, but you want to apply it. What you want to pass to recur length is the rest of the list, right? The cooter of the list.
Yeah, I'm trying to remember how we did that. It was, I
So
thought
the form
that
of this is, well, okay, how do you go down into the REPL and like try to get the rest of 1, 2, 3, 4, right?
yeah, I thought it was just
Yeah, you can do that if you want. You can use single quote. You could also use list. Yeah, either way will work.
oh,
Okay. And it's just warning you that, you haven't run the stuff up at the top, which is fine. You can't. It would blow up at the moment if you tried. Up, 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 up. No. Stop. Go back. What does rest take as an argument? This is what I was talking about the types of procedures can really kind of lead you to thinking better about them. What does rest take as an argument?
takes the list.
It does. So,
Okay, and recur length
what does
is
recur length return? What does recur length return? A number.
we don't know yet.
Well, okay. We kind of have to make the assumption that the function does what it's supposed to do. It returns a number, so you don't want to try taking the rest of recur length. What you want to do, if you look up at factorial, for instance, the form of this is going to be quite similar to that, right? To the form of factorial, actually, right? Which is we want to call recur length again. We want to add 1. You can also just think about it in terms of the definition. It's 1 plus the length of the rest of the list. How do we get using recur length? We just have to pass recur length the rest of the list as its argument. Okay.
Oh, right. Okay. Yeah. Oops. Let me just get rid of this here. List.
Okay.
Because that's the list. I don't know.
Okay. So here, I'm gonna again, like I said, you got pretty far. This is good. But I'm gonna kind of like take over a little bit. So just backspace up to that open paren. You could actually keep the RE if you wanted to, because you're gonna type in recur length right now.
Okay.
And then open a new paren and call rest on LST. And now close up your parens. And keep closing them. And now give it a try.
So now I need to. What am I testing here?
Just pass it a list.
Okay.
Okay, so it works.
Well, how's it then? Just the lists, Oh, I guess before when we did list, it was it was giving us back the list.
Right, we're not calling the list function here.
Yeah.
We're calling rest on LST. So again, what we're doing is we want to repeatedly, let's think about the definition and then think about translating this into code. I think this is more just like a little bit of you still being a little bit just awkward with code. I don't think this
Hmm.
is necessarily a difficulty with recursion. It's just a little bit of a difficulty with code.
Yeah.
Because it's like you need to turn this definition into code. And so I'm saying the definition. 1 plus the length of the rest of the list. Okay.
Hmm.
So when we talk about the length of the rest of the list, let's just use the length function, the length procedure that's built into Scheme here. Okay.
Hmm.
What is the length of the rest of 1, 2, 3, 4? How would
The
you write that? Well, it is
oh
okay, but how would you actually write it at the REPL?
um
And don't write the rest out. Don't write it out. Like, let's say you don't know how to. You're not smart enough to look at 1, 2, 3, 4 and figure out what the rest of it is. You need to use functions to do that. I mean, I know you are, but like, let's just say in this fantasy land, right? So, well, no, length. Length is the first thing, okay? Because let's think about types here, okay? We are looking for the length of something. We want to get a number back. And that means that length has to be the thing that we're evaluating because that's the thing that returns us numbers. That's what I mean about the types being important, right? We know we
hmm.
want a number here. So we know the length is what we're actually evaluating at the outermost level because that's the type that we want, right?
Yeah.
Length. Okay. Now, what does length take? What type of thing does it take?
Takes a list.
It does take a list. So we need to give this something that's a list. REST turns out very handily to give us back lists. We know that, for instance.
Hmm.
Okay. So if we want to get the length of the rest of it, you can just literally type rest here, right? Open paren,
Yeah.
open paren, yeah. And then 1, 2, 3, 4. We do want it in a list, though. Rest takes lists, not numbers. You do need the parens to make a list. There. If you're going to quote a list, you have to put like parens around it, right? Yeah. And now one more paren. Okay. So that's what we're doing here. So, but do you see what's happening there?
Yeah, it's I mean, I don't know if this is how it actually works on the computer, but there's 4 items in the list. That's the innermost parens, and it takes the rest of that, which takes throws out the first item
Yep.
or whatever it does with the first item,
So that
and then
evaluates to the list 2, 3, 4.
evaluates and there's 3 items in that, and so that's
And
the
that's what
furthest.
you're passing to length. That's what you're
Yes.
passing to length. So, right, if you want to get the length of the rest of a list, this is how you write it. You go length of the rest of the list. The argument to length is a list. That list is produced by calling rest on a list, right?
Hmm. Hmm.
So that's the same thing that's happening up here on line 20, right?
Rest of the list. Yeah, it's just generalized. LST is the variable that hasn't yet been passed a value.
Right. When we write the procedure, we don't know what that value is going to be. Now,
Yeah.
note that LST, if we call recur length with 1, 2, 3, 4, like you did there, at different times, like recur length got called a number of times. And each time that it got called, LST was bound to something different. What values did LST take on when this was called?
Well, let's see. Um, recur length if empty list and do to 0, but it wasn't empty. It had 4 items, so it goes to the second branch plus 1. Rest of the list, the recur length is 3, so add 1 to that. Does it only just do it one? If I go to the innermost here, list is 4. Rest of list is no. List is 4, so the rest of that is 3.
List is not 4. List is a list of things. Okay. So the first time you call list, right? The first time you call recur length, you call it with a list containing 1, 2, 3, 4. Okay.
Yep.
Now, that list is not empty, right? So we get down into the second branch.
Mm-hmm.
So we say we want to add 1 to something. We don't know what that something is. We're going to call recur length with something. What do we call recur length at that point with? What is it that we pass to recur length as an argument?
The rest of the list of the rest of 4.
No.
Or
It's the rest of 1, 2, 3, 4. What is the rest of 1, 2, 3 of a list containing 1, 2, 3, 4?
Yeah.
It's a list containing 2, 3, 4.
Yeah.
So it's not 4, it's a list containing 2, 3, 4. So that's what we call recur length with, is that list containing 2, 3, 4. And what happens when we do that, when we make that second call to recur length?
It goes to the second branch again and add 1 to the rest of 2, 3, 4, which is 3, 4.
Well, add 1 to the result of calling recur length with that as an argument, right?
Yeah. Right. Yeah. Right. Gotcha.
Yep.
That's what loops it back.
Basically,
Yeah.
Yep. That's, it invokes the procedure again.
But
it is not technically a loop. It is very much like a loop, but
it's strange.
this is a little hard for people at first. As I said, recursion
its length is never even in the thing.
Right, we're writing our own length function. We're not calling length. We're calculating the length ourselves. Right?
Yeah.
Scheme could lack a function for getting the length of lists, and we could write this way. If we needed it, if like Scheme didn't have that, this is how we would write it. Right? If we had length to work with, we wouldn't need to do any of this. We just call length, right?
But I don't know. How does it know that it wants you to report to print this as an integer, as the number?
Well, it's not really. We're not doing any printing here. This is just the REPL telling us what the function evaluated to.
Evaluate it as the output.
Because let's really think about what actually. I mean, it just tells you, just like anything else. Like we had that odd 10, even 20x, right?
Mm-hmm.
If you call that with 3, that whole if statement evaluates to a 10, right?
Yeah.
And then we know, that's the body of the procedure that we're defining. And procedures, this is why I was being, you remember how I was kind of going through this earlier, exactly like this? Going through this exact same set of things of talking about like what things evaluate to as you go up through the chain of things that are nested, right? In terms of their subcomponents. This is why, is because this is actually really important to understand. We have a procedure and we're going to evaluate that procedure, and it's going to evaluate to something. Well, it's going to evaluate to whatever its body evaluates to, right? So in this case of odd 10, even 20, that's an if statement. Well, what does an if evaluate to, right? Because now to know what the procedure is going to evaluate to, we have to know what its body evaluates to, because that's the rule for what a procedure evaluates to, right? Is whatever its body evaluates to. So its body is an if. So we're not done yet. We have to know, like, what does an if evaluate to, okay? Well, an if is going to execute, it's going to evaluate one of its 2 branches. And the whole if is going to evaluate to whatever the branch that it evaluates to. And that's a lot of uses of evaluate there. But do you follow that, what I was saying there?
Yeah, I mean, just that it evaluates the way that I think about it, evaluates the branches, and which is the one.
It evaluates one of the branches. It only evaluates one of the branches.
Well, I mean, how does it, when in the recur length list?
Okay, I'm just talking about the if here, though, right? I'm talking about odd 10, even 20. Let's not move on from there until we're very clear about what I'm saying about that, okay? Like, don't bring extraneous things into stuff when you're trying to, zero in on a point. Like, stay on that point. So the point is odd 10, even 20, right? Because we want to talk about this first so we can generalize it to the recursive procedures. Mm-hmm. Because it's the same set of rules, and that's the important thing to understand. It's just exactly the same set of rules. And once you kind of see how those literally apply, that literally applying them does it, it will become clearer. But when we have this odd 10, even 20 thing, and we pass it 3, like, that whole thing evaluates to 10, right?
Yeah.
If you were to type that into the REPL right now, odd 10, even 23, like, in parens, apply that to 3, the whole thing would evaluate to 10. And you would see the REPL print that out. You're not printing it, right? We put in print lines earlier and we did some printing, but we're not printing anything there. We're just writing a function that evaluates to a value, okay? When you put something into the REPL, this is the rule with the REPL. When you put something into the REPL, it evaluates that thing, and then it prints whatever it evaluated to. That's the REPL doing that. So the printing is really, really like completely extraneous to what we're talking about, right? We're talking about a procedure that evaluates to a value. And when we call recur length with the list 1, 2, 3, 4, it evaluates to the value 4. And it happens to print that at the REPL when you put it into the REPL, because that's what REPLs do, right?
Yeah.
But it's the evaluating to a value part that's important. So let's take a look at recur length and see what happens when we pass it 1, 2, 3, 4 as a list, right? Maybe to make this simpler, we'll just pass it 1, 2, 3, just so that there's one less step, right?
Sure.
So we're going to pass recur length this list 1, 2, 3, and we do this. And so recur length, we invoke recur length. An environment gets created with the name LST bound to the value 1, 2, 3. A list containing 1, 2, 3, right?
Yeah.
That's what LST is bound to. So the first thing that recur length does when you invoke recur length basically evaluates its own body, right? And what its body is an if statement.
Yep.
That if statement, the way the rules for evaluating that if is, it checks its condition. And it says, okay, is LST empty? So we know that LST is bound to the list containing 1, 2, 3. We say, okay, is that empty? And of course, that returns false. It is not empty. And that means that the if evaluates its second branch. So we go down there and we say, we're going to add 1 to something. We don't know what that something is yet, but it is the result of calling recur length, of invoking recur length again, right? And we say, okay, so we're going to invoke recur length, and we're going to do it with the rest of the list, the rest of LST. So the rest of LST is a list containing 2 and 3.
Yep.
So we invoke recur length again with a list containing 2 and 3. And so we get a brand new environment with LST bound to the list 2, 3. And again, you're talking about how does it know to loop to the top. It's just when you invoke recur length, which is what we just did, what does recur length do? It evaluates its body, right?
Yep.
That's the rule. That's the rule. And its body is an if. And the if is saying, is LST empty? And so LST, we're in this new environment that got created when we invoked it a second time. It is a new invocation, so it's a brand new environment. And in this environment, LST happens to be bound to the list containing 2, 3. So it's not empty. So we say, okay, we're going to evaluate this second branch again. And again, it's like we're going to add 1 to something, which is the result of calling recur length with the rest of LST, which we just said is bound to 2 and 3. So, okay, we're going to call recur length with the list containing 3. And again, we invoke recur length. We get a brand new environment where LST is bound to this list containing 3. That's not empty. We go to the second thing. We say, we're going to add 1 to the result of calling recur length with the rest of this list containing 3, which happens to be the empty list, right? The rest of a list containing 3 is the empty list. So we're going to call recur length with the empty list. We're going to say, yes, recur length, it's the empty list. And recur length of the empty list. We go up there, and again, the rule for evaluating recur length is you evaluate its body. And its body is this if. And the if says, is the empty list empty? And it says, yes, indeed it is. So it returns a 0.
Yeah.
And it does not, I'm sorry?
The true state, it goes to the first branch.
Goes to the first branch. That's right, the base case. It hits the base case. And note that we don't call recur length in that branch, right? So we're done, right? We're just done. All of our work is done at this point because we know what this is. It's a 0. We don't have to do any more work to figure it out. It's just a 0, right? So okay, we're going to pop back up out into the most recent function we were in. We pop right back up into it because we're waiting there to do something, which is to add 1 to something. And we didn't know what that something was. That something is a 0. So we add 1 to that, right?
Yeah, I guess that was the last.
That was the last one when it was like the 3, right? It was the 3. That's where we are now. LST is bound to 3, the list containing 3 at the moment, right? Because we popped up 1 level, right? We had the empty list. We pop up 1 level and it's the list containing 3. We were waiting to do that. So now we pop up another level. We're still waiting to do something. And that thing that we are waiting to do is add 1 to something. So what are we adding 1 to now? Well, we're adding 1 to what we just calculated, which is in fact 1. So now we're going to return the value 2. Okay, so you might have missed a step here. We were in the case where the list was empty, and we returned a 0 from that, right?
Yep.
So we were sitting waiting to add 1 to something. We added 1 to that thing. So that's 1, right? 1 plus
Well, I guess my intuition is to say like we're working in lists, so it would actually return a new list of 1 0 or 1 3.
it.
You know.
Okay, let's think about what it did then. Let's go back down to that case. Okay, so
Yep.
this is the case where LST was the list containing 3,
Yep.
right? So we're evaluating that last branch, and what does that last branch say? It says add 1 to something, right?
Mm-hmm.
The something is the result of calling recur length with the rest of LST. What is the rest of LST?
Empty list.
The empty list. So
Yeah.
we're going to add 1 to the result of calling recur length with the empty list. We get in there, we hit the base case, and we return 1. We return 0, right?
Yep.
So that's what I'm saying about how these things evaluate to things. That whole if evaluates to a 0, right? And because the if is the body of the recur length procedure, the entire call to the procedure evaluates to what the if evaluated to, which is a 0.
In that last nest.
In that last nest, but that's all we're talking about right now is that last thing. So now we pop back up to the thing with the 3, and what we said is we said we're going to add 1 to the result of calling recur length with this stuff. Well, we just called recur length, and we just said that it returned 0.
Mm-hmm.
We just said that's what it did. So it's not returning a list. It's not doing any of that. It returned a 0. And that's what we said is we said, well, what we're going to do is add 1 to the result of calling it. And that thing was a 0, right? So we are adding 1 to 0.
Function. Yes, I got it now.
Okay.
Right. It's the add symbol. Yes.
The add symbol. That's what our branch says. It literally says it. It says add 1 to the result of calling this. And we know what the result was. It was a 0. So now we're returning a 1 from this invocation. The one where it was the list containing 3, right?
Mm-hmm. Mm-hmm.
Okay, so we're returning, which makes sense because the length of a list containing 3 is in fact 1. Okay. So that gives us some faith that what we're doing is correct here. So we pop back up into the previous invocation, which was where the list equaled 2, 3. It was a list containing 2 and 3, right?
Yeah.
And here, again, we are still trying to evaluate this second branch. We put off doing the addition because we didn't know what we were adding 1 to. We knew we were adding 1. It's like, okay, this is plus 1 and then something. And it was the result of calling recur length with the rest of the list, which was the list containing 3. Well, we just talked about what that evaluated to, and it evaluated to 1.
Yeah, right. Initially to 0 and then to 1 when we did the next level and added a 1 to it. So now we're at 1.
Yep. And we're adding 1 to 1.
Yep. Yep.
And that gets us 2, which makes sense. That is what this should evaluate to because we're evaluating the length of the list containing 2 and 3. So,
Well, that's the thing that's odd to me, though, like that we're evaluating the length of it. But
well, we're not evaluating the length of it.
Yeah.
We're attempting to produce the result, right? The function, we're evaluating a procedure, right?
yeah,
It
It's
evaluates to something, and that's what is the number, right? It evaluates to a number. Because think about it, the length of a list is indeed a number, right?
sure.
Okay. So if you write a function that calculates the length of a list, you write a procedure that calculates that. When you invoke that procedure, invoking that procedure has to also evaluate to a number, right?
Mm-hmm. Yeah.
And everything in here does. Because note that there's only 2 branches to the if, right?
Mm-hmm.
And we know that like a procedure evaluates to whatever its body evaluates to, right? And with the proper substitutions made for the names, right? And in this case, the body of this procedure is just an if. So whatever that if evaluates to is what the procedure itself is going to evaluate to, right?
Mm-hmm.
And this if has 2 branches, and what it it's going to evaluate one of those branches, and the whole if will evaluate to whatever that branch evaluated to, right?
Yeah.
Okay.
Yeah.
So these 2 branches, one of them is a 0, so that's for sure a number, right? We know that if it evaluates the first branch, it's going to evaluate to a number, right?
Yeah.
And then the second branch is a plus, and plus always evaluates to a number. If plus doesn't evaluate to a number, it's an error, right? Like if you passed it plus 1 And a list, for instance, that would be an error, right?
Yeah.
But if plus does an error, if this does evaluate to something, we know it's going to be a number too. So you got that first branch, you got that second branch. We know that both of them evaluate to numbers. So we know that if always evaluates to a number. And so we know that recur length itself, right, is always going to evaluate to whatever its body, which is that if, evaluates to. So you can look at it and you can say recur length always evaluates to a number. It can't evaluate to anything else. There's two options when you, well, there's three really. You could call it and it could run forever. But that can't happen with recur length. There's no way to turn this one into an infinite loop because there's no like negative list or something, right? You can get errors though. You could call recur length with 5, and that's going to blow the fuck up because you're going to try to take the rest of 5 eventually, right? You're going to get down and you're like, actually, no, it's going to blow up before that. It's going to blow up on the call to empty because you can't call empty with a number, right? So try calling recur length with a 5.
Recur length of just 5, not
Just
a
5,
list.
not a list containing 5, just a 5, right? Just to make a point. Oh, okay. I'm a little surprised. What happens if you call empty on 5? This surprised me. What happens if you call empty on 5?
Whoops,
Yeah, don't edit. Don't edit the top.
How did that go up there? I guess it was
Oh, it jumped you to where the error occurred.
Yeah, got it.
Yeah. Okay, so try calling empty on 5. Oh, all right. I guess it lets you do that. I'm a little. All right. So I guess I just did that. All right. Empty will actually allow you to call it with numbers. It's just like, yes, this isn't the empty list, right? This actually makes sense. Empty is not just checking to see if a list is empty. It is checking to see if the thing you pass it is the empty list. And you're actually allowed to pass it numbers. They're not the empty list, right? Okay, fair enough. So it's the rest that blows up here, right?
Yeah, because rest is that part of the body of the recur length.
Yeah, that's the first place that you get to where it's like, oh, I can't deal with a number, right? Like we knew it was going to error somewhere. I was thinking it would error on empty because I guess I'm just not all that familiar with Racket. But like, it didn't error on that. It was fine with that, but it's certainly not going to be fine with rest because it just doesn't make any sense to ask for the rest of 5, right?
Yeah.
That has to be a list, and you can even see like this is probably a little hard to read if you're not sort of familiar with it. But you see where it says expected. It's expecting that, and this is a list. And it's not the empty list. That's what it's basically saying. It's saying, I expected this would be a list and that it would not be the empty list, right? And so in this case, it failed that list part. It was like, 5 is not a list.
Yeah.
So yeah. I'm sorry?
Well, I mean, it seems like, the value that the list that the recur length evaluates to in the function of whatever you pass it is, well, the procedure, the recur length procedure is like, this rest piece. It's like the rest is taking the one away and the one over here is putting it back together, to then just report to you. I don't know. I'm not sure what I'm trying to say here.
Kind of, but let's note, though, here's the thing. We want to do some addition here, and note that the rest of a list is not a number. It is a list, right?
Right, sure.
Right, so it's not really like it's not doing a symmetrical operation here. It is making it one smaller in a sense, right? But it's not a number, right?
Yeah.
So...
It's kind of...
This one often takes people a little bit to get. There is something about recursion for some reason, even though it is just, it doesn't, like, to me, it doesn't seem like it should be hard, really, because, of course, I've understood this for, God knows, 25 years or something, right? Like, I do remember having a little bit of difficulty with it at first, though, and we will get to some slightly more complicated examples of this. It turns out you can do some quite interesting things with even with just pretty simple recursion like this. Where it gets really, really important, for instances like operations on trees. There are a lot of things that would be quite hard to write as a simple loop that when you want to operate on trees that are quite that are just much easier to write recursively than to write as a loop. But I'm trying to think here. But there is something about it that tends to give people trouble.
Yeah, I think we're right in terms of saying that it's actually like, for me, it feels more like the coding language or something in it than the actual property of recursion, you know, um, within the procedure. I'm just trying to like, and the one I'm grappling with recur length is the fact that it's actually like, I mean, to look at it and say like, oh yeah, it's gonna return or evaluate and return the length of the number of items in the list.
Well, the length of the list, right? Which is the number of items in the list.
Mm-hmm.
Right.
Okay.
Sorry, I'm being very picky about terminology here because sometimes it's very helpful to be. It's this thing about being very literal, right?
Mm-hmm.
Part of being very literal is being very precise.
Right. Well, that's the term. That's the definition of length. So yeah.
Yeah. And that is well, except that that's a tautological one, right? To say that the definition of length is the number of items in a list is tautological, and you can't, if you don't have a built-in length, that's not a definition a computer can work with. You have to be able to define it because you're defining it in terms of itself. Then it's a tautology, and you can't really hand computers tautologies, right?
Mm-hmm.
You need to hand them something that they can actually work with. You need to hand them something that is defined in terms of things that they already know the answer to. And that's the whole thing about tautologies. Yeah. Recursion is not tautology, right?
Mm-hmm.
It's different from a tautology. You are defining something in terms of itself, but you're defining it. You have to be doing it in such a way that you are using operations that the computer actually has and knows how to work with. REST is one of those things.
Yeah.
The computer has REST. We have that to work with. Addition is also a thing, and we have that to work with. So can we define this in terms of addition and REST?
Yeah. Well, in the addition of one, because the rest is the lists in the absence of the remainder of the first item,
Right. It's right, because the length of the rest of the list is one less than the length of the list itself.
Mm-hmm.
Right.
Mm-hmm.
So that's why we're adding one to it. Right.
Yeah. Building it back up. Yeah.
Yeah. Cool. And are you familiar? I mean, it's almost 11, so we'll pretty much call it here. It's 11. Are you familiar with mathematical induction, though?
Not as a term. I don't know if I am or not.
It's a proof technique, and it's interesting because it's the mirror image of recursion. It's the same idea. So I'll just give you an example, like the outline of mathematical induction, and maybe we'll actually look at this and prove some property of the real numbers. But let's say I want to, not of the real numbers, of the integers, of the positive integers, because that's typically, that's where induction tends to get used a lot. And it turns out that there's this big branch of math that is devoted to the properties of numbers, right? What things are true of discrete numbers, of integers, right? Discrete math is what we tend to call it. It's not discrete with two E's. It's not something you're trying to hide from your wife. It's it does have two E's, but there's a T between them. It's discrete, two discrete things. So we talk about discrete mathematics. It's an important branch of mathematics and computing. It also includes probability, for instance. Probability is a branch of discrete mathematics. But number theory is another one. You're trying to prove properties of the integers, things about integers. So let's say that I want to prove that a certain formula holds true for every positive integer. Okay. Mm-hmm. So one thing I could do is I could check them all. But that generally takes too long, right?
Yeah.
So there's another way of doing it, which is to say it's two steps. You prove that if this property is true of a number, it will also be true of that number plus one, right? Mm. You just find a way to prove that. You find some proof of this. Usually it's an algebraic thing where you're substituting in that number plus one in this algebraic form, right? You do some algebra. So you come up with a proof of that one thing, which says, I have proved that if this is true of a number, it will also be true of that number plus one, okay? Mm-hmm. Now, I prove that that thing is true of I prove that that thing is true of 1.
Yeah.
Well, I've now proved that it's true of all of the positive integers, right? Because we know that if it's true of 1, it has to be true of 2, right? Because we proved that.
Yeah,
We know with the plus 1 part. Well, we also know that if it's true of 2, it has to be true of 3, right? Because that's that thing. We proved that if it's true of a number, it's also true of that number plus 1. So we know then that it must be true of 4, and it must be true of 5, and it must be true of 6. Do you see what I'm saying?
Oh yeah.
Yeah. So that's induction, and it's kind of the mirror image of recursion, actually. They're very similar ideas.
But yeah, founded on the plus 1, proving it at the plus 1. There's the magic.
Yeah, there's the magic. And in this case, you're kind of working it the other way around. You're working it from the base case, right? But it's it's the same kind of idea, and we will see. Definitely save that buffer, right?
Yeah.
Before we get off, save that buffer. At some point fairly soon, we will introduce you to the wonders of version control, but not quite yet. Not quite yet.
The buffer is the top part?
That buffer is the top part, yes.
Okay.
I mean, they're both buffers. The REPL is in a buffer too, but it's specifically, the top buffer. Let's save this code.
Yeah.
We'll want to come back to it. So I will say this about this, by the way. Recursion is something that a lot of people do have some difficulty with. I would say it's typically introduced in most... I mean, it depends on the comp sci program, right? At MIT, when they were teaching out of SICP, obviously they introduced it very, very quickly, like week 2. Maybe even week, boom. But, where I went to school, for instance, this was something that they kind of introduced right at the end of the first semester, and people kind of often didn't really get. And then it was taken up, like, with quite a bit more seriousness in the second semester. So, I mean, this is stuff that even people who are like, I'm going to go study computer science often actually struggle with for a while. So, don't feel bad about it if it takes a little while for the penny to completely drop. There is most people do have this thing where suddenly have kind of a recollection of it, where suddenly the penny does drop and they kind of remember that. They remember, there was this point at which suddenly it all made sense to me. And that's a pretty common thing when looking at recursion, is that it's kind of mysterious until it isn't.
Yeah, right on. I mean, like I said, this in the factorial, that's pretty. That feels quite intuitive.
Well, that's good, because even the factorial like tends to confuse people a little bit. One of the things we'll start getting into is, like, for instance, one of the things that we'll probably try next time is, can you write the function list, list? Well, I don't know actually if we'll write that one. But do you remember map? Right, we don't know how to take multiple variables at this point, so that one doesn't make sense. But if you remember map can be written recursively. So we may take a look at that. Cool. The other thing is, it might make sense to take a look at, so SICP's first examples of recursion are if you add, SICP moves fast. So I feel like you want to have a little bit of a handle on recursion before you try to learn recursion from SICP, basically. Right? Like, it's, again, it's pitched at a very particular audience in very particular circumstances. It's pitched at incoming freshmen at MIT who are going to be devoting a lot of time to it, and who can go to their TA's office for office hours and get together with their friends and are like, laser focused on it. And so SICP tends to be a little bit... SICP is generally too hard for most people to learn to program from directly, I would say. It's a great book if you already kind of know how to program, if you know a fair bit and you want to solidify a whole bunch of ideas. But it's just a little too hard for people to just, like, teach yourself programming in 21 days. It is not. But it's got some great examples in it, and some of them are really, really cool. And so we'll probably want to take a look at some of those too. And they have a really great discussion of, like, this whole thing where we were talking about, like, is the process... Right, the difference between a procedure being recursive, which just means that it calls itself, and a process being recursive or iterative, which has to do with the work being left over, right? These are truly recursive processes because we have work left over that we still have to do as we come back up through the functions. We still have to do those additions. And that means that we're using memory for this, right? That is to say, there is memory being used for each of these invocations, which is not a big deal when we're trying to calculate the factorial of, like, 1. But if you're trying to calculate the factorial of 100,000, you've got 100,000 invocations. You're using memory for all of those environments because you have to hang on to those environments to be able to do the work that you still have to do, right? Because you have to bottom out before you can do any of the work. Remember how I said you don't do any multiplication in factorial until you've already hit the base case and you start coming back up.
Sure.
Well, it turns out...
Building your nest. You're just building your nests there.
Exactly. You're building your nest just like a little birdie. But it turns out there's a way of turning these inside out so that there's no work left to be done. And scheme implementations are smart enough to not use memory. They're smart enough to know they can throw away the environments if there's no work left to do. And so that's a technique that we'll look at, tail call elimination. A lot of languages are not smart enough to know that, and so you will indeed run into big problems if you write recursive functions that get called many times, regardless of how you write them. But it's an important concept, so yeah, we'll take a look at it. But this was good. We got started pretty late, but this was productive. I've been kind of waiting to get to recursion. This is something that it's the first really interesting idea that you hit, I think.
I don't know, man. I like the other ones too. It was cool, and even just I feel like kind of going back through the conversation. I'm sure I'll get more efficient in terms of how to play with stuff once I actually have a little bit of grasp on things, as opposed to just like repeating it over and over again. But even doing that, like just listening to it and hearing the terms and kind of using, it was kind of interesting driving along and using my mind's eye until the snow got a little bit too much. And I'm like, oh, wait a second, that's right, I'm listening to this. I was focusing on the road and shit. But yeah, no, it's good. I'm looking for it. It's a fun mystery to see where we go.
Okay, cool. Well, that was fun, and I will talk to you next week.
All right, very good.
Okay, bye-bye.
Bye.